மது சார். மது சார்.
சார் 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 சொல்லுங்க.
சார் இப்போ யூடியூப் லைவ் கொடுத்துட்டேன்.
ஓகேங்க சார். ஜபசிங் கால் பண்ணுங்க.
சார்
சார் சார் சார் சொல்லுங்க. ஜபசிங் சார். ஓகேங்க சார். சார் ஜபசிங் ஹோஸ்ட் கொடுத்துருங்க.
சரி சார். இப்போ உள்ள வந்துட்டாரா?
இன்னும் வரலையே அவரு. சார் சார்
சொல்லுங்க சார்.
சார் இதுல இந்த டைட்டில் வந்து ரீசன்ட் அட்வான்சஸ் இன் கெமிக்கல் சயின்சஸ் இருக்கு.
எதுல சார்?
இந்த யூடியூப்ல மாடர்ன் ட்ரெண்ட்ஸ் இன் கெமிக்கல் சயின்ஸ் போடுங்க சார். மாடர்ன் ட்ரெண்ட்ஸ் இன் கெமிக்கல் சயின்சஸ்.
ஓ சார் இப்போ மாத்த முடியாது. ப்ரீவியஸ்ல மாத்திட்டேன். சரி சார் நான் ட்ரை பண்றேன் இப்ப. அது எனக்கு
மாடர்ன் ட்ரெண்ட்ஸ் இன்
அதை என்னோட இமெயிலுக்கு மெயில் பண்ணுங்க சார். 901 என்னோட ஐடி நம்பர். பாத்துறேன்.
லிங்க் எங்க இருக்குது
சார்? அங்க மேல தெரியுதா லைவ்னு சொல்லி?
ஆமா, அந்த லிங்கை கிளிக் பண்ணிடுவா.
அது மேல கிளிக் பண்ணாலே இது வருதா, காப்பி ஸ்ட்ரீமிங் லிங்க்னு?
ஆமா ஆமா ஆமா, ரைட்.
அதை அப்படியே பாஸ் பண்ணிட வேண்டியதான்.
அப்படியா? சரி, ஓகே. காப்பி ஸ்ட்ரீம் லிங்க். ஓகே. ஆமா
அது லைவ் ஸ்ட்ரீம் வருது பாருங்க ஜெபசிங்.
Yes.
Live stream on YouTube.
I have taken. எவ்வளவு டிலேல வருது? நான் பேசி 1/2 மணி நேரம் ஆச்சு.
இல்ல சார், நீங்க இப்ப ஆன் பண்ணதுனால வரும். அவ்வளவு டிலேல வராது.
இங்க கேக்கும்.
சரி, இப்ப உங்களுக்கு ஹோஸ்ட் கொடுத்துறவா?
கொடுங்க.
சார், இனி நீங்க வெளியே போகாதீங்க. ஜெபசிங் சார். ஜெபசிங் சார்.
Yes, I am here only. நானும் மது இருப்போம்.
சந்திரசேகர் சார்.
Yes, can you hear me?
கேக்குது சார். சார் நான் வெளியே போறேன்.
Okay, okay.
நீங்க வந்து இதுல இருந்து வெளியே போயிடாதீங்க, அந்த யூடியூப் லிங்கே மாறிடும்.
சரி. Okay.
Venkatakrishnan sir, good afternoon.
Jamasingh sir.
சொல்லுங்க கிறிஸ்டோபர், சொல்லுங்க கிறிஸ்டோபர்.
இப்ப இந்த டிஸ்கிரிப்ஷன் அதுல போட்ட பாருங்க யூடியூப்ல.
ஒன் செகண்ட்
இருக்கும்.
மாடர்ன் ட்ரெண்ட்ஸ் இன் கெமிக்கல் சயின்சஸ். கரெக்ட்.
அது மாதிரி யூடியூப் லிங்க் கீழ இருக்கும் பாருங்க சார், ஃபீட்பேக் ஃபார்ம். அது கீழேயே பாருங்களேன், ஃபீட்பேக் ஃபார்ம்னு சொல்லிட்டு அந்த லிங்க் இருக்கும். இருக்கா?
இருக்கு.
ஓகே சார், நீங்க கடைசியா அவங்ககிட்ட இன்ஃபார்ம் பண்ணுங்க, கிளிக் பண்ணிக்குவாங்க.
இப்பயே கொடுத்துட்டீங்கன்னா அது உடனே இது பண்ணிடுவாங்களே, அது கொஞ்சம் ஹைட் பண்ணி வைங்க.
எப்படி சார்?
யாரு? இல்ல, அது வந்து அதுல யூடியூப்ல பாக்குறவங்க வந்து உடனே பண்ணிடுவாங்க. நம்ம உள்ள வந்தோடனே பண்ணிட்டு வெளியே போயிருவாங்க. அது நம்ம கடைசி வந்து தான் பண்ணணும். நாங்க பண்ண முடியுமா? இதுல சேட் பண்ண முடியுமா?
உங்களுக்கு சேட் பண்ண முடியும். இல்ல, நீங்க அந்த ஃபார்ம்ல கூகுள் ஃபார்ம்ல தானே கிரியேட் பண்ணி வச்சிருக்கீங்க.
ஆமா,
அதை ஆஃப் பண்ணி வைக்கலாம்ல. அப்படிதான்
எனக்கு டிலே வந்து கேட்டுக்கிட்டே இருக்குது. 2 வாய்ஸ் கேக்குது எனக்கு.
என்னோடதா? இப்ப கரெக்டா கேக்குதா?
ஆமா, அதாவது ரெஸ்பான்ஸ் ஆஃப் பண்ணி வச்சிடலாமோ?
அந்த ரெஸ்பான்ஸ் இதை ஆஃப் பண்ணி வச்சிடணும். ஆஃப் பண்ணி வச்சுட்டு உங்களுக்கு தேவையான போது ஆன் பண்ணிக்கணும்.
ஓகே, நான் ட்ரை பண்றேன்.
ஓகே சார்,
நான் ட்ரை பண்ணி பார்க்கிறேன். அதுக்கு எனக்கு ரைட்ஸ் இல்ல ஆக்சுவலா. அதுக்கு வந்து சாம்சங் சாருக்கு தான் ரைட்ஸ் இருக்குது.
சரி சார், அப்ப அவர்கிட்ட சொல்லி அந்த மாதிரி பண்ண சொல்லிடுங்க.
சரி, ஓகே. இப்ப இது வந்து சேட் பண்ண முடியாதுல்ல? ஹலோ. பாப்பா, நீ எனக்கு டிஸ்டர்பன்ஸா இருக்கு. இங்கேயே 2-3 கேக்குது. ஹெட்போன் போட்டா
Dr. Jabbar Singh, good afternoon.
Sir, good afternoon, sir. Good afternoon. Dr.
Hey, good
Sir,
afternoon.
good afternoon, Vijay Kumar. Vijay, good morning, sir.
So how many have joined? As of now, 60 have joined.
Yes, sir.
How many registered, Jabbar Singh, sir?
It is 556, sir.
Oh, good. Dr. Madhav, good afternoon.
Good afternoon, sir.
Good afternoon. Good afternoon. All set?
Yes, sir. Vijay sir, good afternoon.
Dr. Vijay, you are not audible.
Vijay sir.
Sir, Madhu sir, how?
Good afternoon. Now it's okay. Now it's okay.
Oh, okay, health is okay. Okay, fine, great.
Samson, good afternoon.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon, sir.
Samson sir, good afternoon.
Good afternoon, Madhu, sir. Good afternoon.
Samson, sir, good afternoon.
Good afternoon.
Good afternoon, sir.
Good afternoon. 64 join பண்ணாங்க. பஸ் சார் ஸ்பீக்கர்ஸ் வந்துட்டாங்களா?
Dr. Madhu, unmute.
Good evening, sir.
Good evening, Dr. Victor. Prabhu.
Good evening, Prabhu. Good evening.
Good evening, sir. Good evening, sir.
மது சார் அன்மியூட் பண்ணுங்களேன். மது சார்
unmute பண்ணிட்டேன் சார். Unmute. I unmuted.
இந்த மியூட்ல
சார்
உங்களுக்கு மியூட்ல இருக்கு உங்களுக்கு.
Sir, good afternoon, sir.
மேடம் குட் ஆஃப்டர்நூன் மேடம்.
Good afternoon, Dr. Parameshwari.
Good afternoon, sir. Good afternoon, sir. மியூட்ல போட்டுணுமா சார் ஃபர்ஸ்ட்ல?
இல்ல மேடம் இருக்கு ஒன்றும் பிரச்சனை இல்லை. நீங்க தானே மேடம் எம்சி சொல்லிருக்கீங்க.
சார் unmute தான் சார் இருக்கு. ஓ ஓகே.
Dr. Madhu, shall we start?
Start, sir.
Dr. Jabbar Singh,
Yes, sir.
shall we start?
Yes, sir. We can start, sir. We can, madam. We can ask madam to start, sir. Yes, sir.
Dr. Parmeshwari,
Yes, sir.
you can start the meeting now.
Yes, sir. Yes, sir. Good evening to one and all. I welcome all of you, our respected Dean, sir, and faculty members and the resource persons for the National Webinar on Modern Trends in Chemical Sciences, organized by the Department of Applied Chemistry, Karunya Institute of Technology and Sciences, Coimbatore. As we are going to start this meeting with the three important sessions with the three different resource persons. To start with that, we'll start this meeting with the prayer. I'll invite all of you to close your eyes for a word of prayer. Father, we thank you for this time of learning. Oh, Father God, we thank you for gathering all of us, oh, Father God, in this fashion for this national webinar. Father God, we pray that all the participants and along with us, oh Father, and the resource persons, oh Father God, Lord, help us to learn from the resource persons' lectures, oh Father. Father, we pray that our hearts will be receptive to learn, oh Father. Thank you for this wonderful opportunity of learning, oh Father God. We give you all the glory and honor. We pray that, oh Father, that these 2 hours of learning will be fruitful to our student community as well as faculty members. We commit everything at your precious feet. We thank you once again, oh Father God, for this time of learning. In Jesus' name we pray. Amen. Now I welcome Dr. V. Madhu, Assistant Professor, to give the welcome address.
Dr. Venkatakrishnan, IIT Mandi, Dr. Anandu Sellamuthu, Research Scientist, University of Hull, UK, Dr. K.V. Pawan Kumar, Principal Scientific Manager, GVK Biosciences, Hyderabad. I warmly welcome you for your acceptance, and I warmly welcome you to this national webinar on modern trends in chemical sciences, and all the faculty members from all over the nation, different institutions, all the research scholars, all the BSc students and MSc students. I warmly welcome you to this national webinar on modern trends in chemical sciences organized by Department of Applied Chemistry, Karunya deemed universities. And also I welcome our faculty members and our research scholars and all other participants from national and international side. And I hope you'll enjoy this webinar in a wonderful way. And with this, thank you, Dean sir and all the faculty members for giving me this opportunity.
Thank you, sir. Now I invite our respected Dean, Dr. C. Joseph Kennedy, Dean of School of Sciences, Arts, Media and Management, to give the inaugural address.
Good evening to all of you. This is Dr. Joseph Kennedy, Dean of Science, Arts, Media and Management, and the head of the Department of Applied Chemistry. And I'm extremely happy to be here on the day of our national webinar on modern trends in chemical sciences. And this idea we conceived 10 days before, and I handed over this task to Dr. Madhu and Dr. Jabbar Singh along with our team members. And they have floated this national webinar promotion through all the social media, and it was a tremendous response.
Hello.
Sir, can all of you mute your audio so that it will be clear? Whenever you want to say something, if you can unmute and then tell. Otherwise, it would be nice if you can mute your audio. So today the national webinar is taking place based on the plan that we had. I'm extremely happy that the three eminent speakers have come today to deliver their expert lectures. And I am also joining with all my faculty members in welcoming Dr. Venkatakrishnan from IIT Mandi, Dr. Anbu Sellamuthu, research scientist, University of Hull, United Kingdom, and Dr. KVP Pavan Kumar, principal scientist, GVK Biosciences Private Limited. I know how difficult it is because all of them are in very high place and very high reputed institutions. You must have a lot of things to do, but even then you have given some time to the academia and they have spared your valuable time. And I am extremely happy in welcoming all of you for this national webinar, and also all the participants. Almost more than 500 participants have enrolled. Tremendous response. And I thank all the participants as well as the institutions, those who have allowed them to participate in this webinar. So coming to the topic of the webinar, National Webinar on Modern Trends in Chemical Sciences. Nowadays, chemical science emerged as a basic and latest tool for all kind of technical research, education, whether it is technical education or any other basic science education. Chemical science become an emerged area. Chemistry plays a key and vital role for all basic branches of sciences. Day by day, various techniques and instruments encompassing innovations are rapidly emerging in the field of science and technology. Modern sophisticated instrumentation techniques plays a key and reliable role for the characterization, structure determination, and identification of the new molecules. On the basis of these inventions, researchers can modify their work according to the need of the industry and serve for betterment of the society. So ultimately, our aim is also, the University, Karunya Institute of Technology and Sciences is also focusing on solving the human problems. Our thrust area is, university's thrust area is in 4 directions. One is food, another one is health, another one is water, and then last one is energy. So the department's activity is focused towards, chemistry department is also focusing towards the 4 focal areas of the university, and we are working in these directions. And chemical sciences, there is no end to it, and there is no even the some of the branches, they may not require chemistry, but you cannot live without chemistry. The one cannot do any research without chemistry. So everybody has to understand it properly. So that is why the recent trends in chemical sciences needs to focus on all areas in which chemical sciences is applied rather than revolving around our basic science. It is better. It's a time to open up and go to the areas in which the chemistry can be applied exactly. That's what we have to find out. And I am sure that all the three speakers will focus in that direction so that all of you, those who have participated in this national webinar, will take this transformation of knowledge that is going to happen through this national webinar and work yourself along with your team in seeing that how chemical sciences can be applied to all fields, engineering, medicine, everywhere, how it is going to be applied. So nowadays the focus is all applied research. So ultimately, whether your research lead to a process or a patent or a product, that is what the aim. So of course, basic research is also required, but at the same time, the basic research has to escalate into a product level or a process level, finally into a patent level. Then only we will be successful in this competitive market. So all the chemists keep this in mind and work towards the advancement of the chemical sciences. And this platform, this national webinar platform, will be a useful tool in order to achieve your goals in the area of chemical sciences. With this, I once again welcome all of you for the national webinar, and I deeply appreciate the team working behind this national webinar headed by Dr. Madhu and Jabba Singh, and also the entire faculty member of the Department of Applied Chemistry for their valuable contribution. Once again, I thank all our external speakers for spending your valuable time and going to discuss various aspects of modern trends in chemical sciences to the participants. Thank you very much and enjoy this webinar. And at the end, you are free to ask questions as well as the program, whatever the program schedule is going to say, you can freely ask questions and then give us your valuable feedback so that in the days to come, we will improve this Zoom platform webinar so that still it will be more effective. Thank you once again.
Thank you, sir. Now I invite Dr. V. Vijaykanth, Associate Professor, to introduce the resource persons.
Dr. Vijay, unmute your audio.
Yeah. Dr. Venkatakrishnan is ready. May Dr. Venkatakrishnan?
Yes, yes, I am ready.
Yeah. Oh, okay, great. Yeah, great. Yeah, it's welcome. It's my privilege to introduce Dr. Venkatakrishnan. So he did his BSc and MSc from PSG College in Coimbatore. Then he did his PhD in physical chemistry in University of Stuttgart in Germany. Then he moved for his postdoctoral fellowship for the University of Pennsylvania, USA. Then he worked as the research associate in NIMS, National Institute of Material Science. Later, he joined in 2012 as a faculty at IIT Mandi, and now he is associate professor. There is a very big list, is a long resume is there. So because of the short of time, I will just tell a few things. He has got so many awards from DST Inspire Faculty Award, and then IIT Mandi Foundation Day Award, and the MA Research Fellowship, that is Materials Nano Architectronics Research Fellowship. I think it is from Japan, if I am correct. It's then
Yes.
DOE Postdoctoral Fellowship, and the DFG Doctoral Fellowship, and DAD visiting DAAD Visiting Scholarship Fellowship. And it's a long list. It's a long list. It's really, we are happy to have you here, sir. It's very happy. And he has published, he is working in a broad area of research from material chemistry to X-ray science, and he has published more than 80 research articles. So he's already he has 4 PhDs and 8 MScs has been awarded from his group. At present, 8 PhD and 7 MSc students are working with him. He is having a large experience in various areas of the field. So it's working. It's at present. I hope he will be studying. He will be stating about the heterogeneous catalyst for energy and environmental application in this lecture. We welcome you, sir, once again. Thank you. Thank you for giving the opportunity.
Yeah, thank you very much, Dr. Vijay Kumar, and thank you, Dr. Jabasingh and colleagues, for your kind introduction and also for your kind invitation. So I'll be happy to deliver this talk. So let me share my screen now.
Yes, Professor, please use share your screen.
Yeah. Is it now visible? Is my screen visible now?
Yes, Professor, it is visible.
Visible. Okay. Yeah. Thank you very much once again. So today I would like to give a talk about the our research area, which is the rational design and development of nanostructured heterogeneous catalysts for energy and environmental application. And before I start my scientific talk, I would like to acknowledge and I would like to thank my entire research group. So they are the people who have done all the work, and this is the current research group, and some people from my former research group also participated in this research. So I would like to first of all wholeheartedly thank my research scholars for all the hard work that they have done. And the main research focus of our group deals with the nanostructured heterogeneous catalyst, mainly about its design and development. And in this particular area, we are focusing on the photocatalytic water splitting, which is one of the energy applications, the photocatalytic pollutants removal, which is an environmental application. So today I'll be mainly covering these two applications in my talk. And perhaps at a later time, when I get another chance or something, I can cover the other areas of our research, which we are working on as the biomass conversion to valuable products, the bio-inspired scaffolds for dip catalysis, the catalyst for green organic synthesis, and also we study in situ reactions of the catalyst in action. And in the photocatalysis area, the main idea is to utilize the total solar spectrum. And when we see the total solar spectrum, it is broadly classified into ultraviolet region, visible region, and the infrared region. And as you can see in this slide, about only 5% of the total solar radiation is in the ultraviolet region, whereas 43% is in the visible region, and it is also the highly intense solar intensity region, and about 52% is in the near infrared region, which is between 700 to 2500 nanometers. So the main idea of our research group is how we can utilize the total solar spectrum. And mainly we want to utilize the visible region and also the infrared region. So in one of our work, the first work which I'll be presenting, so we worked on photocatalytic water splitting, and we wanted to utilize earth abundant materials and which are low cost in nature, and also which can be used for the water splitting. Water splitting, as we already know, water is this H2O, and H2O is kind of split into hydrogen and oxygen, and the hydrogen which is being obtained from this water splitting is used for different other reactions as an energy source. So in this work, we took the zinc oxide material. Zinc oxide is a very well-known semiconducting material. It's a low-cost material, and it's made of earth-abundant elements. And this zinc oxide material has a band gap of 3.37 electron volts, which is active under the UV light, but not under the visible light region. But we can make this material, the zinc oxide, active under the visible light region as well. So what we did was we kind of develop a strategy wherein this nano-sized zinc oxide was doped with varying amounts of MOS2, which is the molybdenum disulfide, and RGO. RGO is the reduced graphene oxide. Now let me give a justification why we chose these two materials. As we know that reduced graphene oxide, this is analogous to graphene, and it has a 2D network type of a structure with this HP2 hybridized carbon atom, and it possesses unique electronic, optical, and mechanical properties. It's kind of another version of the graphene-based graphene material. And on the other hand, when we have the MOS2 also has a 2D structure. So it has a stacked layered structure, and the sulfur atom on the exposed edges of the MOS2, this has a strong affinity towards the H+ ions in the solution, which are subsequently reduced to hydrogen during the photocatalytic reaction. So in this work, what we did was we prepared this material using a hydrothermal reaction. So we started with the GO sheet, which is the graphene oxide sheet. And then we prepared this graphene oxide with the MOS2 nano sheets. So you can imagine the graphene oxide sheet or the reduced graphene oxide sheet as a large carpet on which the small MOS2 nanosheets are like small footmat sort of a thing, which is also a 2D material, which are sitting on onto this large RGO nanosheet. And over and above this one, we deposited the zinc oxide nanoparticles, or mostly the spherical shaped zinc oxide nanoparticle, to prepare this ternary nanocomposite, which consists of these three components: zinc oxide, MOS2, and RGO. And first and foremost, when we prepare a material, we need to find out whether the material is successfully prepared or not. And so in this regard, we study the X-ray diffraction pattern of this material. So this X-ray diffraction pattern shows that the zinc oxide is successfully formed, and we prepared the nanocomposites in varying composition, right from 2 weight % of MOS2 and RGO till about 10 weight % of MOS2 and RGO. And in all the cases, we are able to clearly see that the zinc oxide materials diffraction patterns could be evidenced. And from XRD, we cannot clearly see the MOS2 and RGO's presence, because this is available in very small quantity, like 2 weight % or at the most 10 weight %. So it's a small quantity, and also there are not many prominent breaks in MOS2 and RGO. And hence we had to resort to Raman spectroscopic technique in order to identify the presence and what is the constituent of the MOS2 and RGO. So we confirmed that, okay, our material is successfully prepared and the composites are successfully made. And now we need to see what is the morphology of the composites. I was telling you about this large sized carpets, and on which the small footmats are existing, and over which there are certain balls of the ZNO which are put on it. So we want to see whether it is actually formed in this way. So in order to study that, we use the transmission electron microscopic technique, as it is shown here. These are the TEM images. This image shows the formation of this GO. And this is the image which indicates the presence of RGO. It's a bigger carpet, and on which the MOS2 nanoparticles are present. And this is the HRTEM image, which shows the intimate contact between the MOS2 and RGO. And this is the zinc oxide nanoparticles, and this is for the composite. We took up a particular composite, which is the 4 weight % composite. So, and we can clearly see in these images, a very good heterojunction is being formed between the three materials: the MOS2, zinc oxide, and RGO. And this heterojunction is very important for the photocatalytic activity, which I'll be explaining in the subsequent slides. And apart from the transmission electron microscopy studies, we also did the EDAX analysis in order to identify what are the consistent elements which are present, constituent elements which are present in the sample. Then we did a very detailed XPS analysis in order to study the electronic structure and the composition of the elements, which are shown here. We studied at each of the elements in detail. And because of the lack of time, I'm not going into too much detail into the studies, but if there are questions, we can take it up at the end. And subsequently, we did another characterization, which is the DRS, the diffuse reflectance spectroscopy. So this characterization clearly tells what is the absorption of this material. So we can see that the zinc oxide is absorbing only the UV radiation, as it is already very well known. Whereas this composites from the entire range of the composite, which contains the MOS2 and the reduced graphene oxide, this is started to absorb also in the visible light region. So we can clearly see the absorption in the visible light region, and these are the photographs of the sample, which clearly indicate the color of the samples. Yeah, any question? Sorry. Okay. Then, as I said, we also did a detailed Raman spectroscopic analysis because we want to see that whether the GO is converted to RGO in the material. So this can be identified with the shift with the ratio of the DNG bands. So we did that analysis in order to study that. And subsequently, we also did the TGA study, the thermogravimetric analysis, in order to study the thermal stability of the composite. And we evidenced that the composite is quite stable even at a very large temperature of about 300 or even beyond. And subsequent to a very detailed characterization of this material, we tested this material for the photocatalytic water splitting reaction, or rather photocatalytic hydrogen evolution reaction, because we are also using a sacrificial agent. And these are the results which have been obtained from the photocatalytic hydrogen evolution reaction. And we did it for all the different composites in addition to the corresponding control samples. And we found that the 4 weight % sample gave the best result. It showed a very high hydrogen evolution of about 28.616 millimole per hour per gram under the direct sunlight irradiation. So all these experiments were done in our lab under the direct sunlight irradiation conditions. And these are the results which have been obtained. And we also studied if we vary the amount of the catalyst, how the results vary. We studied and we found that even a very little amount like 3 milligrams or even the 5 milligrams of the catalyst can give quite good hydrogen evolution. And we also studied the recyclability of the catalyst, whether the formed catalyst can be recycled, for how many times it can be recycled. So we studied it for 5 cycles, and we found that without any loss in the activity, the catalyst was performing very well. And now we wanted to understand why this catalyst is so good and what is the reason behind its high performance. And in order to understand this, we studied the recycled catalyst, or the catalyst which is recovered after the 5 cycles of recyclability. And we studied typically the morphological analysis, and also we did the structural analysis using X-ray diffraction. And interestingly, we found that during the process of this catalytic activity, the zinc sulfide is being formed under in situ condition. So this is a very interesting finding, and this zinc sulfide, this plays a synergistic role, and it plays a very positive role in the photocatalytic hydrogen evolution by increasing the number of transfer interfaces. So now the number of transfer interfaces is increased, like zinc oxide, zinc sulfide, zinc oxide, Mos2 and RGO. And when the number of transfer interfaces increases, the charge separation also increases. So there is a in the photocatalytic activity, it's mainly because the electrons jump from the valence band to the conduction band. And once it jumps to the conduction band, it has to, that electron does the reduction reaction, and the holes which are found in the valence band, that needs to be eliminated. So the sacrificial agent is being used here. The sacrificial agent used is the Na2SO4 with Na2S, and this sacrificial agent kind of consumes the holes and allows the electron to do the reduction reaction. And this photocatalytic process, or the charge transfer process, this has to take place in a longer duration of time. Longer in the sense it might be around femtosecond or picosecond duration. And this number of transfer interfaces increase in this number increases the charge separation, and this aids in the photocatalytic activity. And the detailed mechanism of this, whatever I explained, is shown in this figure, where there is a zinc sulfide, zinc oxide, Mos2 and RGO. And this provides a very clear picture about the reason behind why this material shows a very good photocatalytic activity. And this work was published in the year 2017 in this journal, ChemSys-Chem. And subsequent to this work, our group also did several other works on the zinc oxide based materials, and I'll just highlight a few of them. And due to the lack of time, I'll just mention about the few of them. So the previous work I talked about, it contains a ternary material, which is a 3-component material, and we used a direct sunlight. Whereas in this work, we used a 2-dimensional nitrogen doped zinc oxide and graphitic carbon nitride nanosheets, and we again used it for the photocatalytic hydrogen evolution. So we, from a three component system, we came down to a 2 components system. And this material also gave a very good photocatalytic hydrogen evolution, and this work was published in this International Journal of Hydrogen Energy in 2018. And in the last year, we also published another work on hydrogen evolution. So here we introduced defect-rich Mos2, and the defect-rich Mos2 is again a very interesting material, because as I mentioned earlier that the exposed sulfur atom in the Mos2, this plays a very important role in kind of this acts as a sticky end for the H plus ions. So if there are more such sticky ends, like more such exposed sulfur atoms, this will be highly beneficial. So in order to introduce this more such sulfur atoms, we introduced a defect-rich Mos2. And this defect-rich Mos2, along with the nitrogen doped zinc oxide, the nitrogen doping of zinc oxide, that plays a role in shifting the valence band to a slightly higher value. So this will help in reducing the band gap and thereby easily enable the promotion of an electron from the valence band to the conduction band. So we did this work, and we again observed a very interesting results for the photocatalytic hydrogen evolution. And this work was published in ACS Applied Energy Materials last year. And based on our work done on the zinc oxide based materials, both in terms of the hydrogen energy as well as in terms of environmental remediation, we published a review article very recently, and this was published in Catalysis Reviews. And now moving on to the next topic of my presentation. So now we wanted to move to a different type of a semiconducting material. So we chose calcium titanate, because calcium titanate is an oxide perovskite material. And this material, calcium titanate, is again made of earth abundant element, and it is a relatively low cost material. So what we did was we took this calcium titanate material and we doped this material with nitrogen. And the reason for doping this nitrogen is we can tune the band gap of this calcium titanate material. And calcium titanate is also quite a well-known photocatalytic material, but in the UV region. But we wanted to make it active in the visible light region. So we took this calcium titanate, doped it with nitrogen, and then supported this material on RGO, the reduced graphene oxide, and we used it for the pollutants removal. And interestingly, this particular material can do the work in two ways. One is it can absorb the pollutant, because the RGO has a much larger surface area, as I told you about this carpet type of a thing. So it can absorb all the pollutant, and subsequently the calcium titanate can play the role of a photocatalyst and do the photocatalytic degradation of the pollutant. So that's what we did in this work, and we studied it with using two different pollutants. One is methylene blue, another is thiabendazole. The reason for our studying with two different materials is the methylene blue is a colored pollutant, and colored pollutants, as we know that this has a very strong photosensitization effect, and it would be relatively difficult for us to quantify whether the photocatalytic effect is due to the photosensitization of this dye, or is it because of our photocatalyst. So hence we tried also a colorless pollutant, which is the thiabendazole, and studied its degradation. So this can clearly indicate to us that whether the activity is because of the sensitization or because of the photocatalyst, because here there is no role of photosensitization. And similar to the previous work, we did a very detailed characterization of our material. So we studied the X-ray diffraction pattern of the calcium titanate, and we also studied the X-ray diffraction pattern of the nitrogen doped calcium titanate, and the different samples which are containing RGO in different ratios from 1 weight percent to about 20 weight percent. And we also studied the Raman spectroscopic analysis to further support the structural characterization. And we also studied this TGA, the thermogravimetric analysis. So this will provide the information about the thermal stability of our material. And then we studied the morphological characteristics of this material. And in the morphological characteristic, we found that the calcium titanate, this is, has a bricks type of a structure, and in the micrometer scale, as you can see it here. And the RGO, it has a much larger two-dimensional sheet type of a structure. So on the two-dimensional sheet, these bricks are lying around. And we also did the HRTEM analysis to study the kind of close proximity or the contact between these two materials. Then similar to the previous work, we also did a very detailed XPS characterization on this material in order to identify what the electronic configuration and also the oxidation state of the different elements involved and the composition of these samples. And composition might also indicate what type of environment these samples are present. If there is nitrogen, what is the environment of nitrogen? So all those details it was possible to obtain from the XPS analysis. And subsequently, we used this material for the degradation of these two pollutants. One is the methylene blue dye. The kinetics plots are shown here, and the detailed characterization plots are shown in our paper. Someone is interested, we can have a look at our published article. So these are the kinetic plots for the degradation of the methylene blue dye. And you can see that there is a contribution from the adsorption and there is also a contribution from the degradation. So you can clearly see what is the contribution from adsorption. First, the material dye gets adsorbed and subsequently the dye gets degraded. And we also determine the rate constant for each of these cases. And another very important thing in the photocatalytic pollutant degradation is there are several reports on the pollutant degradation. Mainly they study the decolorization of the pollutant. So the methylene blue dye, which has this color kind of like a pink colored solution, after the degradation, it becomes a colorless solution. Similarly, if you take malachite green, it would be green in color in the beginning and subsequently it becomes colorless. So mainly it is the decoloration of the material. But what is important is whether the decolored material substance is really safe in nature or not, and whether this process really leads to the degradation, and the degradation products are toxic or non-toxic. So we need to identify the degradation products. And in order to identify these degradation products, we did a detailed mass spectroscopic analysis as shown here. This is the formula for the methylene blue. And we studied different fragments. What are the different fragments which are found after the degradation? So you can see that these are the different fragments which are found after the degradation. And these fragments are much less toxic compared to the actual methylene blue. Fine. And we also studied, there is a comment here. Please move this window away from, I don't know. Are you able to see the presentation? Is it fine?
Yes, sir. Yes, sir. I can see.
Okay. Thank you. So we studied also the mechanism of the photocatalytic activity in this case. So as it is presented here. So this is the nitrogen induced band, which is slightly above the valence band in the calcium titanate. And because of this, the band gap of the calcium titanate is being reduced. And here in the valence band, the oxidation happens, and in the conduction band, the reduction happens. So because of this reduction, the electrons are available, and these electrons can also degrade the product. And we found that this product has a very good, this catalyst has a very good stability and recyclability. And this work was published in the year 2017 in this journal, Material Chemistry Frontiers. And as a follow-up of this work, we also studied the perovskite structured calcium titanate coupled with graphitic carbonitrate, and we used it for, again, different organic pollutant degradation. Especially we used it for the bisphenol A degradation. So this we studied. And this work was published in Bellstein Journal of Nanotechnology in 2018. And very recently, we used this calcium titanate along with this H sulfur atom enriched Mos2 on reduced graphene oxide. And we studied not only pollutant degradation, but also the photocatalytic hydrogen evolution. And this work was published in this journal, ChemPhotochem, recently. And now moving on to the third and the last part of my talk. So we have been talking about how to utilize the sunlight for the photocatalytic degradation or for photocatalytic application or the visible light. And now I'd like to move my focus on how we can better harness this infrared region of the sunlight, which is about 52%, which is the largest region in the sunlight. So in order to do this, we needed a unique type of particles, which are this upconversion nanoparticles. And this upconversion nanoparticles, these are very interesting type of particles, and these are not really new because these are being used as fluorophores in biomedical applications such as bioimaging and theranostics. But its use in the photocatalysis domain is very limited. And what actually this upconversion nanoparticles does is that these nanoparticles, these are actually composed of a lattice along with some dopants. The lattice is predominantly it's sodium yttrium fluoride, it's the lattice, and it is being doped with ytterbium and erbium, or you can kind of tune this dopants based on any of these lanthanide series materials. And these lanthanide series materials can be either a sensitizer, or it can act as an activator. So it's sensitizer and activator, and by tuning the identity of this sensitizer and activator, you can get different colors. So let me explain how this works. So if the infrared radiation, and as we know that infrared radiation is low energy radiation compared to the visible or the ultraviolet radiation. And in this process, there are 2 or more infrared radiation which are impinging on this material, gets converted into a single high energy photon. So this is a bit different from the conventional luminescence. In the conventional luminescence, as we are well aware, there is an absorption of a light of a higher wavelength, and there is the non-radiative decay, and there is a emission of a light of a lower wavelength. This is the conventional luminescence, which most of us are familiar with. Whereas in the case of upconversion, we are upconverting the spectrum. So there is a multiple absorption which is taking place. So there is an first absorption and the second absorption, which could be due to the different infrared light sources. And then there is an emission, and the emitted light has a higher wavelength compared to the absorbed light. So hence this name upconversion comes. So in this work, what we did was we chose a particular upconversion nanoparticle, especially a green light emitting upconversion nanoparticle. As I said, the upconversion nanoparticle can absorb the infrared radiation, and the visible light radiation is emitted. And by tuning the identity of this lanthanide dopant, you can tune the color of the visible light emission. If you have ytterbium and erbium, the visible light emission will be in the green color. If you have ytterbium and holmium, it will be in the red color. If you have ytterbium and thulium, you will have the visible light emission in the blue color. So you can tune the color of the emission. So in this work, what we did was we took this upconversion nanoparticle, the sodium yttrium fluoride with ytterbium and erbium, which can emit green color. So we took this upconversion nanoparticle and coated it with a shell. So this is a core shell type of a nanoparticle. So the core is the upconversion nanoparticle, and the shell is another material. And what we did was we chose this shell material as cadmium sulfide. So the cadmium sulfide, why cadmium sulfide? Because cadmium sulfide is a very interesting material. It's a semiconducting material, and this cadmium sulfide has a band gap of about 2.4 electron volts, and this region falls in the green light region. So if it is falling in the green light region, so whatever is the emitted green light from the subconversion nanoparticle can be absorbed by the cadmium sulfide. So when it gets absorbed, then this cadmium sulfide, since it is already a semiconducting material capable of doing photocatalysis, so the photocatalytic activity can be done using this material. So that's how we can kind of best utilize the infrared light from the sunlight region. And what we did was we further decorated this material using gold nanostars, and because the reason for using the gold nanoparticles is that this can do the plasmonic enhancement, and also we know that the gold plasmonics is also active in the infrared region, so we can kind of further enhance the photocatalytic activity. And this entire material, we supported it on RGO, the reduced graphene oxide, and the reason for supporting it on RGO is a good electron acceptor, it's a good electron transporter, and also it provides a large surface area for the adsorption of the pollutant. So hence we used this RGO here. So, and similar to the previous work, we also prepared a series of nanocomposites ranging from 1 weight percent of RGO to 5 weight percent of RGO, and we fixed the gold weight percent to 2 weight percent. So it is not a lot of gold which is being used, and cadmium sulfide was already used in this case, and also sodium yttrium fluoride is used as the lattice. So, and we did prepare the different composites, and we tested the composite using different techniques. So first comes the XRD technique. Normally we use the XRD technique to understand whether the synthesis was successful or not. And we studied this XRD. So we can study this for individual cadmium sulfide, individual graphene oxide, and also for the gold nanoparticles, and subsequently for the upconversion nanoparticles, and also for the composites. And we confirmed that, okay, whatever we desired, we are able to prepare that. So we were successful in preparing this nanocomposites. And then we wanted to study the morphology of the nanocomposite. And we studied the morphology of these materials using scanning electron microscopy. So you can clearly see what type of nanoparticles, so homogeneous, same sized nanoparticles could be formed. And this is for the nanocomposite. I'll show you better images in the TEM. So in the TEM, we are able to see it much more clearly. So these are the core shell nanoparticles, which can clearly see that there is a dark colored core, which is the upconversion nanoparticle, and which is surrounded by this light colored material, which is the cadmium sulfide. And we also did the HRTEM analysis in order to see what is the contact, whether a heterojunction is being formed or what type of junction is being formed. So that we studied using the HRTEM measurements. And subsequently, we did studied also the composites, and we can clearly see what type of composites are being formed. And these are the elemental mapping images, which clearly show where which element is present in the sample. So that's clearly shown here. And subsequently, we also studied the DRS. The DRS is the diffuse reflectance spectroscopy. So we can identify what is the band gap, how we are changing the band gap in this material. And also the photograph of the samples are clearly indicated. Then we studied that thermogravimetric analysis in order to prove that our material can sustain very high temperatures as well. And we have been talking about the large surface area of this material. So we did the BET analysis to study what type of surface area we are able to get from these samples. And as mentioned earlier, we also did a very detailed XPS analysis of this sample. And the XPS analysis clearly showed what are the constituent elements and what is the electronic configuration, what is the oxidation state, and how they are kind of interacting with the other elements with their surroundings. So that studies we did. And in addition, we from the XPS, we also studied the valence band spectrum. And the valence band spectrum clearly indicates what is the position of the valence band maximum. And from that, we can experimentally calculate what is the valence band maximum and also what is the conduction band minimum, which are very important parameters in this case. And since we are using the upconversion nanoparticles, we need to study the upconversion luminescence. So how much amount of this infrared radiation and how it is being converted into the visible light radiation. So this is the upconversion luminescence process. And you can see this is the upconversion luminescence spectra. So you can clearly see that when we pass the infrared light, as we know that we cannot see it with our naked eyes. So we have an infrared laser. So when you pass this infrared laser light, you can clearly see when it goes through this solution containing, or rather it is a dispersion containing the upconversion nanoparticles. During this place, you can clearly see what color of emission. It's showing a green color. So this green colored emission is from the upconversion nanoparticles. So this is the detailed upconversion luminescence spectra. And then we used this material for the photocatalytic degradation of a drug-based pollutant, a pharmaceutical pollutant, which is the ciprofloxacin. So this is the ciprofloxacin dye. And as we know that we are also using this reduced graphene oxide. The reduced graphene oxide provides a very large surface area for the adsorption of this pollutant. So when the pollutant gets absorbed, we can study the adsorption using the Langmuir and Freundlich isotherms. The Langmuir is the monolayer isotherm, and yes, we can see from these plots that the Langmuir isotherm fits our data much better than the Freundlich isotherm. So hence it is a monolayer adsorption. And subsequently, we studied the degradation of this ciprofloxacin dye, ciprofloxacin pollutant using the different light conditions. So first we use the visible light radiation. Why visible light radiation? Because we have a cadmium sulfide, and cadmium sulfide can play a very good role in the visible light photocatalytic activity. And we study the visible light radiation. And we also did the adsorption and the degradation component. And these are the kinetics data. And we can see that the one particular sample, the UCAG4, exhibits the best photocatalytic activity under the visible light radiation. So here in the visible light radiation, the upconversion nanoparticles play almost no role at all. On the other hand, when we studied using the NIR radiation, so NIR radiation, how we studied means we have a solar simulator which gives which kind of replicates the sunlight irradiation. So when the light from the solar simulator comes, we can use a band pass filter. So using the band pass filter, we can completely block the UV light and the visible light, and only the NIR light can be allowed to penetrate through the sample. So the NIR light penetrates, which we cannot see, but it really penetrates through this bandpass filter and interacts with our sample. So these experiments have been done only under the NIR light radiation. And as we can see, the UCAG3 sample, this sample provides a very good NIR light catalytic activity. So that's our finding. And subsequently, we also studied the photoelectrochemical studies, wherein we studied the photocurrent and how the photocurrent varies during the on-off cycle. And also we studied the EAS plots, the electrochemical impedance spectroscopy. Mainly, this also called as the Nyquist plots. So we did this studies, and we could also derive an equivalent circuit as shown here. And then based on the entire detailed study, we are able to propose some mechanism for the photocatalytic activity. So one is under the visible light radiation. The visible light impinges on the cadmium sulfide, and the cadmium sulfide does the entire photocatalytic activity as shown here. And on the other hand, in the NIR light radiation, the NIR light falls on the upconversion nanoparticle. And interestingly, the cadmium sulfide shell is transparent to the NIR radiation. So the NIR radiation can penetrate the shell and reach the core, which is the UCNP. And because of this, there is an energy transfer which is happening, which is shown in this arrow. And then because of this energy transfer, there is an excitation here in the cadmium sulfide, and this does the photocatalytic activity. And in both the cases, the gold nanoparticles have a plasmonic effect and shows the SPR effect, and which facilitates or enhances the photocatalytic activity. And in addition to the studying this mechanism, we also studied what is the total organic carbon content and how this total organic carbon content decreases over a period of time during the photocatalytic process. And similar to the previous work, we also did mass spectroscopic analysis in order to study what are the fragments which are formed after the photocatalytic activity and how these fragments could be classified. And these equations clearly state that how the photocatalytic activity process takes place. And this work was published in this journal, Applied SES Applied Materials and Interfaces in 2018. And subsequent to this work, we also even further enlarged the thing in order to have the wide spectrum activity, wherein UV, visible, as well as the NIR, all the three regions play a major part. And in this work, we used a TiO2 based shell, and also instead of gold, we used silver copper bimetallic nanoparticles, and the upconversion nanoparticles also we used, but here we used the different dopants. Here we used ytterbium with thulium, which can show activity under the UV and blue light irradiation. And this work was published in the Journal of Hazardous Material in 2019. And based on our work using upconversion and nanomaterial, so we also did a lot of work on the biological part of the upconversion nanomaterials using through some collaboration in Finland. And that work I am not presenting it today. But overall, based on the upconversion nanomaterials, we wrote a review article which was published in this journal Small in 2018. And finally, to summarize, our group is actively working in the field of nanostructured heterogeneous catalysis, and we work on photocatalytic water splitting, photocatalytic pollutant removal, biomass conversion, bioinspired scaffolds for dip catalysis, catalysis for green organic synthesis, and also in situ studies. Yeah. And once again, I would like to thank all members of my research group, the faculty colleagues and staffs here at IIT Mandi for their kind support, research collaborations both within and outside of IIT Mandi, and also this Advanced Material Research Center, which is our main centralized instrumentation facility for providing all the facility, including TEM, SEM, XPS, and all the facility. And I would also like to mention that our facilities are open for all. So we can receive samples from anywhere in India or even abroad and do the measurements. If anyone is interested to utilize our facilities, they could contact me. I'll put you in touch with our office, and they could mention to you what are the instruments which are available and what are the charges which we are charging for the measurements. And in addition to that, I also would like to thank the different funding agencies, the DST Inspire, HIMCO-STAY, BRNS, and IIT Mandi, ISRO, and SERB for their financial support. I thank you one and all. Thank you.
Thank you, sir. Thank you so much for your valuable lecture on nanocomposites in water splitting and photolytic pollutant removal. It is really very interesting, and we want to thank you on behalf of Department of Applied Chemistry. We thank you. And now I invite Dr. R. Nandakumar, Associate Professor, to give brief presentation on the department facilities of Applied Chemistry Department.
Are there any questions, or we'll take the questions later?
Only one question, sir, in the YouTube. Just will ask, what is the efficiency of photocatalytic water splitting? That was asked by Narugopal Manna.
Okay.
Yes, sir.
That's a very good question. So, interestingly, in these works, whatever I presented, we haven't calculated the STH or the VTH efficiency. The STH stands for the solar to fuel, and VTH is the visible light to fuel efficiency. So we haven't calculated because we didn't have the facility to calculate that quantum efficiency in this regard. But in some of our future works, we are doing that calculation for the efficiency, but we haven't got huge efficiency. Our efficiencies are somewhere around 10% or much lower.
Okay,
So
thank you. Thank you, sir.
Sir, another question from our MSc student over here in Karunya. She is asking that when we dope with the nanomaterial on the graphene oxide, how the band gap is get tuned?
Yeah, that's a very good question. So when we dope this material, for example, in two of the works which I presented, both the works we have doped the nitrogen on the zinc oxide or nitrogen on the calcium titanate. And when we dope this material, so the band gap usually depending on what the dopant. So what is the dopant? Whether it is an electron donating dopant or an electron taking away dopant. So there is a P-type and N-type semiconductor doping strategy. So we can choose the dopant, and because of the dopant, you can either increase the valence band maximum. So there is a valence band, you can increase the valence band maximum, which we have done it in our case, wherein we did dope with nitrogen. Whereas if we dope with some other element, we can minimize the conduction band minimum. So there is a conduction band, and you can minimize the conduction band minimum. So, so overall, the process of doping kind of either increases the valence band or minimizes the conduction band. And the main objective is to bring the reduce the band gap, and also to tune the position of the valence band and the conduction band. So this is the process how the doping helps.
Yes, sir. Another question is probably you are taking that the graphene oxide, which is the sheet one, and you are doping on the top of this. My question, doping the top of that nanomaterial. What is this the interaction? Okay, it is covalent in not non-covalent interactions. What would it be if it is a covalent interaction with that graphene oxide with any organic precursors? Is there any idea?
Okay. Yeah, in most of these works, there are all normally non-covalent interaction. So there are no real covalent interaction. And this one thing. And I would also like to distinguish between doping with composite formation. So the doping is we are kind of inserting an element in the lattice structure. So we are making changes in the structure. Whereas in the nanocomposite formation, we are just combining the materials in certain ways. Either it could be due to electrostatic, or it could be due to this hydrothermal thing. So we are combining these materials. And in this combining the material, there is no change in the crystal structure of the material. So it is only we are making a composite of this material. And in order to see, we could go from the HRTEM. We can see that these materials are kind of closely sticking together or closely attached together, but these are attached non-covalently. So there are no covalent interaction. It's predominantly the electrostatic type of interaction. But it is important that these materials are touching each other so that the electron transfer can happen.
Yes.
These are non-covalent, no covalent interaction.
Yes. So in the case of non-covalent, the sustainability will be there, right? Reproducibility and sustainability will be there.
Yeah. And these are not 2 week and they won't separate and all, because they are kind of sticking because of certain reasons. Because of the positive charge on one end and the negative charge on the other end, they are sticking. And even during the recyclability, we are able to still maintain these interactions. So,
Thank
and
you,
we
sir.
have
Thank you,
also
sir.
demonstrated using the recyclability. Yeah.
Sir, I'm
Dr.
Dr.
Vijayakant, please.
Yeah, just excellent lecture by Professor Venkatakrishnan. Thanks once again. Yeah, just you talked about the upconversion. So in that, that
Yes.
means two low energy photons are converted into high energy photon. So in the emission, it will be in the higher energy region. That means it will be in the lower wavelength region, isn't it?
Yes, correct. Yeah. So it would be the higher energy and the lower wavelength. Yes.
Lower wavelength. Okay. And another thing, have you tried any electrocatalysis or only the photocatalysis?
Yeah, our group is mainly working on photocatalysis, so we haven't done any electrocatalysis. In fact, that is not in our domain of research interest. We collaborate with other groups to do the electrocatalytic HER and other things, but we ourselves have not done any electrocatalysis.
Okay, we may be in contact, I think, and because some
Sure.
Indian gallium nitride materials, some materials have been also tried. I think because different materials, the different band gaps are appearing. So which will be for the HER reaction, which will be the better material? So how you the fabricating the tuning the material? So are you working on that? The how to tune the material?
No, we are not working in that area. One is we are not working in the area of electrocatalysis, and secondly, we are not working in indium gallium type of semiconducting material. We normally prefer to work on earth abundant materials which are easily available, low cost, and easy to handle. Whereas indium gallium arsenide or those type of materials are extremely expensive.
Okay. Thank you.
Sir, this is Nandakumar from Karunya.
Hello, Nandakumar. How are you? Good.
I'm fine, sir. Thank you for your presence and a wonderful lecture on the research. Apart from research, just I want to ask you something. Can you tell something motivational
Sure.
for the present MSc students and the forthcoming MSc and the Research College of Chemistry?
Okay. That's a really a good question. I was not prepared with an answer for that, but I can definitely tell something whatever it is in coming to my mind. First, with the research scholars, please focus on your main area of research and try to go more deeper and deeper rather than spreading thin on taking several problems which are not very well connected and spreading thin. Instead of that, take one problem and try to go more deeper and deeper, and try to develop a lot of contacts and networks, and see to that the lack of facilities should never harm your research, or you can always look for several other places where you can do some characterization or something. But I am sure I have visited Karunya, and I could see a lot of facilities over there. So that has a lot of advantage that there are many facilities and you can study many things in well. So focus on one thing and go deeper and deeper. This is my suggestion and advice for the research scholars, which immediately comes to my mind. And for the MSc students, when you study different courses in the MSc chemistry or in whatever courses you are studying, think from how this could be practically applicable. So what is the practical application? So how to do it? So that you can see the practical application. And another thing is focus on understanding the basics of the courses. It's not necessarily for the exams, but see how deep you can get into the basic, why it is happening that way. If it is an electron transfer, or if you are telling, okay, this in the alkali metal chlorides, why we follow this series in the dissolution, why it is happening, how it is happening. So think from all different perspectives and be very strong in the fundamentals and basics, which will eventually help out in the long run. And also parallelly prepare for some competitive examinations like GATE, CSIR NET, GRE, and other examinations, so that immediately after your MSc, usually MSc chemistry is not a stopping course. Beyond that, either it is a research or you end up in a teaching a job either at a school or a college. Think from that what you want to be in. What's your next destination? 5 years down the lane, where do you want to see yourself? 10 years down the lane, where do you want to see yourself? So think from that perspective and keep a direction and ensure that almost every day or every month you are moving in that particular direction. So that will be helpful. So this is my thought for the MSc students. Yeah.
Thank you, sir. Thank you. Thank you very much.
You're welcome. Okay. Good. Yeah, thank you very much. Thanks for I really enjoyed the presentation and the interaction. I hope it's very beneficial to everyone. Thank you. Thank you very much once again.
Thank you, sir. Thank you so much. Now
Welcome.
over to Dr. Nandakumar.
Shall I share?
Yes, sir. Yes, sir. Please.
I'll stop share now.
Hope the screen is viewable to all.
It's viewable.
Yes, Professor, it is you.
Yeah, thank you. So good evening, good afternoon, good morning, ladies and gentlemen, wherever you are across the nation and around the globe. It's my privilege and pleasure to present a brief profile of the Department of Applied Chemistry at KITS, located at the foothills of Sirwani, the Western Ghats, Coimbatore. It's just a decade-old department and offers the following programs: BSc Forensic Science, MSc Forensic Science, MSc Chemistry, PhD Chemistry. So we work for the challenge of global change, where we work on the chemistry for tomorrow's world under the tagline, explore the mystery of molecules and materials. So our vision is to enlighten and enthuse the students academically, ethically, spiritually, so that they are empowered to tackle societal challenges. And our mission is to serve humanity by attaining high levels of academic excellence, professional competence, and exemplary values to find solutions to human problems. So this presentation goes like this, with the academic programs, faculty profile, research publications, followed by funded research projects, the patent published by the department, students, scholars' achievement, and finally the infrastructure and learning process. So as I told earlier, we are offering 4 programs, PhD chemistry, both full-time and part-time, and 2 years MSc chemistry program, both were started in the year 2007. And from this year onwards, we have started 3 years BSc Forensic Sciences and 2-year MSc Forensic Sciences. Besides these programs, we cater to other courses like first year BTech and elective papers, MTech elective papers, and also to the 5 years integrated MSc Nanoscience and Nanotechnology. So this is the credit distribution for BSc Forensic Science. We offer the choice-based credit system, and the total credits is of 140. And it is the split up as shown here: departmental core, electives, projects, general core, and also we have included community and social inclusivity in the curriculum. And it's a technology-related curriculum wherein we have the papers like forensic toxicology, question documents, forensic ballistics, forensic psychology, so on and so forth. So this is the credit distribution for MSc Forensic Science. The total credits is 93, and we have in-house projects, and this is the distribution. And here also we have the community and social inclusivity as a part of curriculum. Apart from that, we have both part-time and full semester projects, and it's also a choice-based credit system. We have elective papers like cybercrime, forensic psychology, biological instrumentation methods, forensic analysis, etc. And also interdisciplinary courses like IPR, ethics, and research methodology, value education, process product solutions, etc. So the eligibility for BSc Forensic Science is the higher secondary, 10+2 or equivalent qualification from a recognized educational board with physics, chemistry, biology, or maths as main subject, and a minimum aggregate score of 50%. In the case of MSc Forensic Science, you require a bachelor's degree in science, forensic science, medicine, veterinary science, dental science, pharmacy, engineering, or equivalent degree with a minimum 50% marks from a recognized university. We have a merit scholarship that is one-time entry-level scholarship for UG program for all Christian candidates, an amount of rupees 10,000 per year. So this is the career prospects for BSc MSc Forensic Science as medical examiner, laboratory analyst, crime scene investigator, forensic auditor, professor, forensic expert, crime reporter, so on and so forth. So this is the credit distribution for MSc Chemistry program. So the total credits, as like MSc Forensic Science, it is 93, and we have in-house projects, and it is also a choice-based credit system. And we have both full semester and part semester projects in the curriculum. So we have elective papers like biomolecular chemistry, materials, supramolecular, medicinal, etc. And we have interdisciplinary courses like chemi-informatics, chemical approach to nanomaterials, molecular machines and materials, entrepreneurship, and a business plan, etc. So we have a unique curriculum in our MSc Chemistry program. 2 labs. One is called the Modern Instrumentation Lab. The other one is the Chemistry in Everyday Life Lab. Both are industry-oriented. So the Modern Instrumentation Lab, wherein the students will be having the hands-on training on these following instruments like UV, photoluminescence, IR, HPLC, GC, XRD, SEM, etc., with the support of Agilent Technologies, JASCO, Bruker, etc. With the help of Pelican Biotech, in the Chemistry in Everyday Life Lab, which is called CELL, students will be able to prepare candles, soap, phenol, paint bomb, tooth powder, even glass blowing, which would be of industry-relevant programs. And the Industry Connect and Internship Fellowship, wherein our students have gone for the past years. This is last year. They have gone for Carborundum Universal Limited in Kerala, Pelican, Achi Masala, Microlabs, Happy Ventures, etc. And this is faculty and staff, captained by Professor Joseph Kennedy. We have 3 professors, 4 associate professor, and 7 assistant professor as a team of Department of Applied Chemistry. All are doctorates, and we are assisted by 3 technical staff. So 4 of our faculty have cleared the CSIR NET, and 5 of them GATE exam, and 7 with postdoctoral research experience. 2 of our faculty have got UGC Research Award, and 10 patents has been so far published from our department. So these are the faculty with postdoctoral experience across the globe. Dr. Vijaykanth from University of Toronto, Canada. Dr. Rajendra Kumar from Texas A&M University, USA. Dr. Jeba Singh from Catholic University and Università di Torino, Italy and Belgium. Dr. Vinu from Czech Academy of Sciences, Czech Republic. Dr. Madhu from Weizmann Institute of Science, Israel. Dr. Emmanuel from Nanyang Technical University, Singapore, and myself from Pahang University of Science and Technology, as well as Eva Women's University from South Korea. So the faculty work on the broad research area, starting from biofuels and textiles chemistry to synthetic organic, supramolecular electrochemistry, fuel cells to inorganic and coordination, and nanomaterial and applications. So far, we have published around 360 publications for a period of 10 years. Among that, 331 publications are Scopus indexed with the highest impact of 14.695. It is the Journal of the American Chemical Society. We have 28 ACS publications and 25 RSC publications so far, at an average of 36 publications per year. So we have received a total grant of to the tune of rupees 6 crores. Out of that, 12 projects have been completed to the tune of 2.3 crores, and 9 projects are ongoing to the tune of 3.7 crores. So these are all the completed projects from UGC, DBT, and DST. And these are all the ongoing funded projects from DST, Water Technology Initiative, CPRI, DST, TSDP, DST, DPRP, SCRB, MR, BR, SDA, etc. And we have submitted nearly 7 projects to the tune of 4 crores. These are some of the project outcomes. From the project, we have got 12 major instruments, 14 minor instruments. We have conducted the science academics lecture workshop, hands-on training for students, 12 JRF and 20 project assistants, and more than 200 research publications out of it. In addition, 3 patents out of the projects. So these are all the Indian patents filed, published, and granted. So Dr. Parameshwari, Dr. Mose Selvakumar, Dr. Emmanuel, and Dr. Samson Nesraj have published Indian patents. And recently, Dr. Parameshwari has been granted with the patent on the title, A Method for Decolorization of Dyeing Wastewater by Electrocoagulation using Titanium Oxide-Coated Aluminum Electrode. And as well as Dr. J. Prabhu and Dr. R. Nandakumar have published, published several other patents. Totally 10 patents from the department so far. So we do the interdisciplinary research at KITS in terms of the projects, national, international research publications, chemical analysis, training and lectures, instrumentations, and knowledge transfer with other departments such as nanosciences, biotechnology, water institute, mathematics, civil, computer science, etc. And this is our proud alumni. Our students are across the globe. Dr. Sri Creation, UAE, and Dr. Sheikh Gus Pereira as an assistant professor in Korea, Dr. Ravichandran as a PDF in Korea, and Dr. Jnana Pragasham in Chile, and then Dr. Chidambaram, Dr. Velmurugan, Dr. Govindan in Israel, China, and Korea, etc. These are all some of the significant achievements of students and scholars. Our students have received a UGC Rajiv Gandhi Fellowship, CSIR Senior Research Fellowship, and then 2 of them have cleared CSIR NET, and UGC Postgraduate Indira Gandhi Scholarship for Single Girl Child, UGC Merit Scholarship, Tamil Nadu State Council for Science and Technology Best Student Project, and have received, the scholars have received Silver Jubilee Fellowship, Postdoctoral Fellowship, National Postdoctoral Fellowship, and they have received the Karunya Short-Term Research Grant, and have received several Best Oral and Poster Awards, more than 60, and so far 31 PhD have been awarded from the Department of Applied Chemistry. We have another unique program called IAST at Karunya. It is called as International Association for Exchange for Students for Technical Expertise, wherein foreign interns come to our department and our scholars and students go to other departments across the globe. So in that, students have come from Germany and Tunisia. Our own students have gone to Portugal and Ghana. So these are some of the faculty who have contributed to the edited books: Dr. Mose, Dr. Juliet Jnanasundari, Dr. Parameshwari, and myself. And many of our faculty members are there in the editorial board, such as International Journal of Chemistry and Application, Journal of Harmonized Research in Applied Science, etc. And many of our faculty are in professional associations, starting from American Chemical Society to Korean Chemical Society to Israel Chemical Society to American Standard Testing Methods, etc. So we have conducted a national conference on innovation in chemistry, health, and energy on 6-7 February 2014, which is funded by SERB India and BRNS. And very notable speakers from India have participated in it and delivered lectures. Similarly, we have conducted the recent advances in chemical sciences in February 18-19, sponsored by the Indian Academy of Sciences, Indian National Science Academy, and the National Academy of Sciences. So very renowned professors from India have delivered their lectures in this Science Academics lecture workshop. Very recently, in the month of March, 4 and 5, we have conducted the International Conference on Frontiers in Chemical Sciences, ICFCS 2020, wherein many renowned professors, both national and international, have come over to our portals to deliver their lectures on their recent research. And it is sponsored by SERB India, AVRA, Polar, INCAP, and the media partner by all Conference Alert and Wix.com, etc. So several professors from China, Taiwan, and Japan were not able to come to our portals, due to the pandemic situations. And these are all a glimpse of the happenings that, of the conference during the time. And we have academic interaction, both national and international, with all these institutes: SICRI, Bardiyar, Periyar University, national and international, with Pohang University, Boha, University of Calgary, Weizmann Institute, etc. And these are the industry interactions with Bruker, Neoscience, Synthite, Biocon, and recently our students have been placed in Syngene also. So these are some of the students' activities. We have a magazine called ChemLight. Every 6 months we release a magazine, and students go for industrial tour wherein they visit many research labs and industries. And our students, because we have the lab called Cell, where they prepare all these bomb, chalkpiece, etc., they take that as an outreach to the nearby villages to teach them as an outreach community. And this is a paper cuttings of that. And this is about the infrastructure and learning resources. This is our research lab, and this is our UG lab, and this is our PG lab. And we have the gas chromatograph, the major instrument, gas chromatograph, IR spectrophotometer, UV visible spectrophotometer, HPLC, biodiesel ransomate, electrospinning unit, electrochemical system, spectrofluorometer, and HPLC mass facility. And in addition, we have the NMR 300 megahertz, which is under installation. And these are some of the other equipments: muffle furnace, rotavaporator, ultrasonicator, centrifuge, flash chromatography, etc. So, well, I conclude. As I once again tell, we offer BSc Forensic Science, MSc Forensic Science, MSc Chemistry, and PhD Chemistry. Apart from that, other engineering, arts, agriculture, and science programs are there. Only a few seats are still remaining in case of MSc and BSc Forensic Science and Chemistry. So there is one thing called as expression of interest in the Karunya website, www.karunya.edu. You can just show your interest there. We will get you back. Once again, thank you all. Thank you.
Thank you, sir. Thank you so much. Now I invite Dr. Jebas Singh, Associate Professor, to introduce the next resource person, Dr. Anbu Chellamuthu.
Thank you, madam, for the opportunities. It's my privilege to introduce my friend, Dr. Anbu Chellamuthu, from our own land, Tamil Nadu. I'm very happy to introduce. Now he is doing the research scientist in University of Hull. Okay, last week when I invite him, and he hardly accepted our invitation. Thank you, sir. Thank you very much. He took his PhD in University of Madras in the year 2010 under the supervision of Dr. Kandasamy, well-known professor in inorganic chemistry. And his research interest is focused on the bioinorganic chemistry. Recently, he is working on the MRI contrast agent for breast cancer imaging. And he holds many awards and honors. It is 2 pages actually. I start from the CSR career, early career, CSR senior, SRF senior research fellow to DST research associate, UGC Kothari postdoctoral fellowship, FCT postdoctoral grant, and European Commission Marie Curie grant, which is meritorious one, visiting researcher in IIT Kanpur, STEM ambassador in the case of UK, and outstanding reviewer award he has received in 2018 from elsewhere journals. Then visiting researcher in University of Hull, UK, and recently he got the grant from RSC, a research grant. It's really a topmost prestigious grant he received over there, and he has published many papers in all the top impact factor journals, and also he has teaching experience, and he to wonder his service to the society. He conducted the breast cancer awareness campaign program in the last year 2019 in village-based women in Tamil Nadu. Okay, really wonderful one. And Young Achievers Award 2018 from Scientific Tamil Award 2019 from Kerala Tamil Sangam, and Ambassador STEM is Science and Technology, Engineering, Mathematics, Ambassador UK representing our country in UK, Marie Curie Association champion. So it's go on increasing. For the font of time, I want to really all the best for Dr. Anbu Chellamuthu's research and his team in UK. And thank you, sir, for accepting our invitation to share your research experience in the title of Basic Sciences Behind MRI, Magnetic Resonance Imaging, which is one of the tools to identify the breast cancer and cancer imaging. Thank you. Thank you, sir. Now you can share your screen. Thank you, sir.
Thank you so much, sir. Thank you for very privileged to be here. So since I'm also from the Coimbatore area, I studied my UG and PG in Coimbatore. So I'm very happy to be here as a resource person. Just I would like to thank you very much for Dr. Jebas Singh and all the department faculty members. I know only before Dr. Jebas Singh, I know in the field of supramolecular chemistry, I am working in chemosensor. So I know Dr. Nandakumar. Thank you very much for this one. I just today only I'm seeing him in person, virtually. Though it's virtual, I'm very happy to be here, and also other professors. Thank you, sir. Because of just let me today I would like to go for very basic science, because of in India it's a magnetic resonance imaging is one of the growing, developing field of science. So I wanted to make many students, particularly we are mostly from the students are from the rural area. So we want to understand what is the real science behind the magnetic resonance imaging, and also then in the future there should be at least some research institutes should concentrate on the development of research on the magnetic resonance imaging. That is very, very important in this stage. It is urgently needed. Just let me start from the Yes, it is visible. Can you?
Yes, sir, it is visible.
Yeah, thank you. Okay, let me start from this. Just basic sciences behind magnetic resonance imaging. Just this is the very, very simplest method, and also this is the powerful non-invasive technique which allow to identify what are the abnormalities inside the body without cutting or without doing any surgery. That is the speciality of this method. So let us see from the history of India. So just the first medical imaging, it was the Susruda was the first surgeon who was believed to be living in between 1000 to 600 BC in India. He was doing surgery for his patients and from his literature that is called Susruda Samhita, is called Susruda's Compendium. So from that literature only we are coming to know he was the first surgeon of India. Then after that, many surgeons were evolved in our country, but throughout the world, it was many surgeons were evolved. However, they were hidden by our many like colonial and other periods of time. So we will come back to the science. So till the 18th century, maybe in the year after 1895. So no surgeons were evolved after the Susruda, and also why only in the 18th century? Because of in the year of 1895, there was the first medical imaging instrument was developed by Professor Roentgen. That is nothing but X-rays. We know that why the name is X-ray, because of the unknown property. We are simply in the like algebra, the unknown things always are represented by X. That's why the rays are unknown rays. There's a very, very high ionizing power. The energy, the X-rays possess the high amount of high ionization potential. Because of that, and also Roentgen was using this the source, particularly this X-rays, and he was produced the image particularly in order to, because of this X-rays can penetrate only the soft tissues, it can penetrate the hard tissues like calcium apatite or like a hydroxyapatite or calcium salts. Particularly, it's all the bones are made up of calcium salts. So these rays cannot penetrate the hard tissues like bones. That's why he was utilizing harnessing this X-rays to image the internal structure of the body, particularly bones. But this is the X-rays are very harmful. We know that it has high ionization potential. Because of that high ionization potential, it can induce the mutation in the particularly cancer cells. Particularly, I am doing studies on MRI. Particularly breast cancer. The breast cancer cells are highly prone to metastasize into the bones because of they need more amount of phosphates, particularly pyrophosphate and ATP. These are main requirement for the breast cancer progression. So because of that, it's need more amount of phosphates. So I was thinking that to develop some pyrophosphate sensitive sensor material as a magnetic resonance imaging contrast agent. So then I thought we have studied the MRI capability inside the breast cancer cells, and we have successful in that. So let us see in the later slides what are the effects what I have studied. So let us start from the magnetic resonance imaging. So because of that very harmful effect of the X-rays, then later days there was the science. The people start to think in differently, and they have invented different imaging strategies. Particularly among them, the MRI is the very powerful technique. So in the year of 1947, MRI was discovered by 1947 by Felix Bolz and Edwards Mills in Purcell. Then after several years, then the first human MRI was developed by Paul Lauterbur and Peter Mansfield and Raman Damadian. So then this is the first MRI picture where the human was the Paul Lauterbur was sitting, and they were recording the MRI using the first machine. So then why the MRI is harmless to the body, why it is a very advantage over the other imaging systems, because the magnetic resonance MRI, we are using only two kinds of harmless sources. The one is a strong magnetic field, the second one is the radio frequency radiation or radio frequency waves. So what happens first, let us see the first magnetic field. The magnetic field is always, we know that is measured in Tesla. Is the clinical MRI performed in between 1.5 to 3 Tesla, and it is very higher than the Earth's magnetic field, that is around 40,000 times higher energy. So this allowed to pick up a car. Just let us see this a small image where you can see that's a very strong magnet they are using to pick up a car. So this much amount of energies, magnetic energy is needed to image the internal structure of the body. So how we are going to image what is the role of the magnetic field? Let us see here. The magnetic field is nothing but about a strong magnet. I said already, the geomagnetic strength is around 2.5 to 6.5 in 10 to the power of -5 Tesla. So, but the magnet in the MRI machine, we are using only 1.5 to 3 Tesla. So it means around 5,000 to 1,40,000 times stronger magnetic field we need to image the body or molecules inside the body. So what is the MRI? This is a symbolic representation of the MRI scanner, where this is the patient bed. There's a platform where the patient is lying inside, and this inside of the inner part of the MRI scanner is made up of coils, particular radio frequency coils. That's also represented as a gradient coil. The gradient coil means we are sending pulse of radiations to inside by after sending the a particular time basis, we are sending a pulse of radiations to radio frequency wave to inside. It will go inside. At the same time, we are applying the very strong magnetic field. Is already we said around 1.5 to 3 Tesla magnetic field we are going to send. So what is happening inside the body? Because just is nothing but we are going to image something molecules inside the body. The molecule is nothing but water. So the imaging in the water inside the body is nothing but magnetic resonance imaging. So why we are imaging the water? Let us see with the examples and applications. So the MRI is allowed to visualize soft tissues including muscles, brain, lungs, and internal organs. All the organs we can image by using this MRI technique. And also it is also MRI. Recent years it has been associated to diagnose the cancer. Particularly we can evaluate the disease progression including cancer. So let us see in the later slides. Then this is the medical MRI. So we know that there are the two kinds of images we can get it. One is the T1 image, and this is the T2 image. This is the bisectional and cross-sectional images we can get it by using this medical MRI. Also we can image what is the progression in the brain functions. Also we can make it as a simple images. Then we can identify or we can understand what is the real function of real function of the brain, and everything we can coming to know by the simple method is a MRI technique. How does it works? So it works based on the NMR. We know already many of we are from the chemistry, so we know that NMR technique, the NMR, how it's work. Because if you're taking a simple example of methanol, if you want to identify elucidate the structure of the methanol, just we are taking in the sample holder. That is this is the sample holder, which is covered by some radio frequency coil. So, and also this both the sample holder is also this covered by the both sides are covered by the strong magnetic field, is nothing but is a magnetic field. So just we here we are insert the sample. For example, if you take the methanol or ethanol, we will take the ethyl alcohol. So CH3, CH2, OH. There are the three kinds of protons are present. One CH3, there are the three proton in one environment. Like it is near to the CH2, there is one environment. OH is near to the CH2, that is also one environment. So each proton has three different chemical environment. Because of that chemical environment, they starts to they can absorb the different amount of radio frequency waves. So because of that absorptions, they will undergo excited state. So when they are excited state, so what is happening? So they will come back to the original state by losing the absorbed energy when we are stopping the radio frequency radiation. So when it is coming out, so the absorbed radiation will come out as it will come out. We are collecting as output, the radio wave output. We are converting, we are using the detector and amplifier. We are converting as NMR signals. So based on the signal, so then we are conforming the structure of the ethanol. I mean CH3, CH2, OH, like that. Similarly, the same principle, instead of the organic or inorganic sample, we are using the human body. The human body, just we are lying inside the MRI machine, where the radio frequency coil, will, our body containing water molecules can absorb the radio frequency radiation. Then they will undergo excited state in the presence of the strong magnetic field. So sometime in the absence of the magnetic field, the protons will lie in the ground state always. So when we are after absorption of the radio frequency radiation, then they will undergo excited state. Then they started to oppose the external magnetic field. Let us see in the later slide what is happening really. So then when we are stopping the radio frequency radiation, then energy will come back. Whatever the absorbed energy will come back to the original state by losing the absorbed energy. That we are converting as signals. That signals we are going to make. The MRI machine is making as simple images. So that is the basic principle behind the MRI technique. So how nothing but water. We know in the whole world, I mean the globe is 70% of world is made up of water. Similarly, our body is also made up of water. There are the different organs contain different proportions of water. That is the very, very important case here. So if you're considering the normal cell and cancer cell, there will be the different amount of water and all the different environment. The water molecules are present in different environment. I mean, a particular amount of water can precise or they can absorb a particular amount of radio frequency waves than the water present in the cancer cells. So that difference is only we are going to studying in the MRI machine. So here, there are the crores and crores of water molecules are present in the body. So in each organ, there are the different proportions, different amount of water molecules are present. So just let us consider only one water molecule. So we know that there is water molecule is made up of 2 hydrogens and 1 oxygen. Oxygen is magnetically inactive because due to the both positive charge, the even number of protons and the even number of electrons, they will cancel each other. But if there is the spinning is cancelling each other. But if you're coming to the proton, so there are the one proton is present in the nucleus. So we are considering as each hydrogen is according to the quantum physics and everything. We are saying that the proton is a small tiny magnets. If you are the charged species with in the stock magnetic field, they starts to spin on their own axis. That is a special property of the proton. So just if we are considering only one proton, so the one proton is nothing but the hydrogen atom. So here the proton is spinning on their own axis. So but how much speed the proton is spinning, that is the very important point we want to know. That within 1 second it completes around 63 crores times. It's very fast. It's we can't imagine that much fast the proton is complete. It's within 1 second it's complete. It's around 63 crores times. That's why we need around 63.9 megahertz of radio frequency wave, I mean energy is needed to excite each proton from the lower energy to the higher energy. So when we are supplying this energy, proton starts to like a spin like a top, you know, in Tamil is a pambaram. So how they can start to spin on their own axis, and also they are do like this. So because of this, when you stop the radio frequency radiation, they will come back to the original state by releasing the absorbed radio frequency radiation. So the relaxation time will differ. That is, that relaxation times are represented as T1 and T2 relaxations. I think you got aware of this spin and spin lattice relaxations in NMR. The same principle here only are applying. Let us see the T1 and T2 relaxations in MRI. So let us see one proton, for example, for in the longitudinal is the T1 relaxation. The proton is lying along the external magnetic field, that may be Z axis. But if you are here, the proton is lying perpendicular to the external magnetic field, that is called as transverse relaxation. Let us see what happens. Just if we are turning on the radio frequency radiation, the proton will flip to the opposite to the magnetic field. I mean, they are undergoing excited state by absorbing the radio frequency radiation. I mean, the proton is flipping. Just I have shown here only 90-degree flipping, but actually the proton sometimes it may oppose, it may flip to the 360-degree also. So just I shown here only is 180-degree. So I shown only 90-degree flipping. So here the proton is already, it was in the perpendicular to the external magnetic field, but they will take around 360-degree rotation. Then this is called a relaxation. What will happen if you turn off the radio frequency radiation? I said already the pulse of radiations only per second or a particular microsecond or nanoseconds we are sending radiation, radio frequency radiation only we are sending inside. So when you are stopping the one after sending a pulse of radiation or pulse of radio frequency waves, when we are stopping the radio frequency waves, then the proton will come back to the original state by losing the absorbed energy. This similarly, so that will come back. That's why I shown only that the 4 lines is coming back to the original state by losing the absorbed energy. So this time needed to realign with the Z-axis in the magnetic field is called as T1 relaxation. But if you come to the transverse, the proton is again after 360-degree rotation. It will come back flipping back to the Y-axis again. So this is called T2. T2 needed realign with X, Y, and axis magnetic field. Sorry. Something, Dr. Mamta Rani, sorry. So this is the T1 weighted image. So from the one side, hello, Dr. Mamta. Dr. Mamta Rani Kaushik, I think there something is song and something is playing. Sorry.
Professor, you please proceed.
Thank you. So T1 weighted image. So from one end of the one ear to the other ear, that is called a bisectional image from the top of the head to the toe. That is called the T1 weighted image. So there you can find a small abnormality or some abnormal tissues, or maybe a cancer. So we can find what is the depth and where there is the abnormalities are present. Everything we can find by using the T1 MR image. The MR, this is called T2 weighted image. Is the cross sectional from the forehead to the back head. So here also we can find it exactly. These are the two relaxations or mechanisms are playing the role to get the different weighted images in the MR. Let us see now we are going to the contrast agent. It is a real chemistry. So this is the contrast agent means, for example, if you want to, this is the some photo. So in order to get only the clear image of this particular desired organ, maybe for here is a flower. So if I want to get this, so I need to use something contrast agent, so that will omit the other parts of the organ. Then we can get interested organ only, we will get imaged by using the contrast agent. Let us see some more with the examples of the images. This is the MR image without contrast agent. So you can't see, you can see only the internal structure of the face with the brain, but nothing. Sorry. This is the MR image with the contrast agent. So where you can find the some small depletions and some abnormalities in the brain as well as in the face. So this is the advantage of the contrast agent. So benefits of the contrast agents. So the contrast agents relies on the distinctive signal intensity of two adjoining tissues. I said already there will be the different tissues contains different amounts of water under the different chemical environment. Because of the different chemical environment, they'll show the difference in the structures. But however, the most of the time the normal and abnormal tissues are frequently overlaps, because due to the similar kind of molecular environment around the water protons. So because of that, we can't differentiate the normal and abnormal tissues by simple MRI. So in this case, we are needed to use the contrast agent that will change the relaxation. I mean, it will alter the tissue relaxation times and manipulate the signal intensity. Mostly it will enhance the relaxivity, enhance the MRI structures. So let us see that. Just this is the symbolic representation of the gadolinium-based MRI contrast agent. So the gadolinium contrast agent, I used to compare with one temple in India, the Tirupati. I think many of you people come to know there is the law. After long hours of waiting, the people will go and see the god. So, but however, after reaching near to the god's place, they won't allow you to stand for few, at least for 1 or 2 minutes. They will allow you to stand within 10 to 20 seconds. I mean, within less than 1 minute, they'll allow you to, they'll make you to go out from that. They will say in Telugu is jarigandi like that. The same principle we can apply here. The strategy we can apply here. So there are the large number of the water molecules are waiting to reach gadolinium. The gadolinium is just, we can think as the god's place. So the water molecules always wants to come close to the gadolinium. Why the water molecules wants to come close to the gadolinium? Because the gadolinium is the one of the very important metal. That important metal, the lanthanide, it has 7 unpaired electrons in their outermost f orbital. Because of this high electronegativity and also they have the magnetically reactive nature, they can attract the positive charge of the water towards itself. Because of this electrostatic force of interaction, the water molecules can come close to the gadolinium, and when they are approaching to the gadolinium molecule, then they can replace the coordinated water molecules, get magnetized. So because of this getting magnetization, the relaxation time will vary. So what is the variations and everything we can see. So because of the very fastly, when the water molecules are getting exchanged from the gadolinium after getting magnetization, so they can get relaxed fastly or they can go very slowly. So according to that magnetization power with a particular as a function of time, so we can get a clear or very bright image or maybe dark image. Let us see in the later slides. So effect of contrast agent in the TN relaxation. So already we know that proton is always lying in the ground state, that is in the align with the external magnetic field. So when you turn on the radio frequency radiation, it will flip to the 90-degree angle. So after that, if you are using, there are the two kinds of relaxation. When you are on the without contrast agent, it will take some time. So because I have given the more number of arrow marks to show it will take longer time to come back to the original state by losing the absorbed energy. But if you see here, if you're using the contrast agent, make the water molecule containing protons to get faster relaxation. I mean, more number of water molecules can get magnetized. It means the more number of water molecules when they are getting relaxation fastly, so we will get it will cover almost all the water molecules in the cancer cell or normal cells. Then easily we can differentiate that will reflect in the image contrastness. So we will get the clear image while you are using the contrast agent. Let us see with a good example. This is the longer T1. This is the short T1. So the short T1 is due to the using the contrast agents. So let us see with a graph, that is the time versus the magnetization. If you are using the longer, I mean without contrast agent. So what happens, the without contrast agent, it is within a time. So see here, this is the time. So within the time, less than time. So it reaches only still it is in the dark region. But if you're using, so here this is the brain image of one of the mice. So there is the relaxivity overlaps, unable to distinguish the normal and abnormal tissues. But if you're using the contrast agent, so it's same time, but there is the magnetization is increased. The percentage of the magnetization of the proton is increased, but at the same time. So, but it reaches the very, very bright images. There you can find some tumor molecules are present in the brain. So this is the real advantage of the contrast agents. So why manganese-based contrast agent? Because of gadolinium is highly toxic. The free gadolinium is highly toxic. So it should not release to our body. It will create very adverse problems, particularly the patients with kidney diseases. So that's why we are interested to develop manganese-based contrast agent, since it has 5 unpaired electron, and also it is a less toxic and biogenic metal, which is essential metal ion for the function of mitochondria. That's why we are developing the manganese-based contrast agents. So this is the manganese-based contrast agent that I have developed, designed, and developed recently here. This is the manganese probe for the MRI, but this is there are the two DPA units that we have incorporated with this MRI probe. So that will is acting as a ATP receptor. So this is the crystal structure of the one with the water molecules. So here this relaxometry data, it shows that upon binding of the ATP, the compound shows higher brightness than the water and commercially or clinically available contrast agent, that is a Manganese, that is a gadolinium-based contrast agent. So biodistribution, so that is the final one that we have achieved some in vivo MRI. That it is the compound is selectively accumulate particularly in the liver and other areas like a kidney area. So it is coming out very fastly within 45 minutes. This is the difference and post and difference between the post and pre-contrast. This is the merged image. This is the heat maps of in vivo MRI. So this is the within very fastly it's coming out, because all the within 45 minutes we have used very, very less amount of 1 milligrams per kilogram, as like that is a very, very low concentrations we have used. So this bladder it shows that more amount of the compound is accumulating in the bladder, such as that it's coming out from the body fastly. I mean, this clearing out. It's and also this compound is highly stable. We have checked with some physiological and transmetallation studies also we have performed. So for the time constraints, I have reduced the number of slides here. So conclusions, we know now what is mean by MRI. So we are MRI is nothing but imaging water inside the body. So the water, each organ has different amounts of water, and they can absorb or they can precise according to their chemical environment. I mean molecular environment in the tissues or in the organs. And also then I shown that why the gadolinium contrast agents are better. Sorry, manganese contrast agents are safe alternatives to the gadolinium ones. And also then what are the studies we have performed, and what are the profiles we have achieved by using this contrast agents. So these are my research collaborations. So this is the University of Hull where I'm doing the research, and this is my mentor. Now he got placed in King's College of London, St. Thomas Hospital as a molecular imaging lecturer. Then this is the government hospital where I am doing a collaborative work for some phantom images. This is Dr. Lawrence, is one of my collaborators. The other collaborator is Dr. Andrea Martin from Germany, who is helping me for, we are collaborating for particularly in vivo MRI contrast agents. And Professor Marabata, he is a very familiar professor in the field of MRI. So we are doing some NMRD studies with this group. And these are the paper recently we have submitted for one of the journals. So let me, I think, hopefully I'm waiting for the results shortly. And I would like to thank all the institutions from my PhD from the University of Madras. Then I moved to the Kothari Fellow. Then I was working as a lecturer in NIT Calicut around 6 months as ad hoc faculty. Then after that, I got a Kothari Fellowship. Then I moved to Professor P.S. Mukherjee in IESC. Then I got my FCT Fellowship with the Professor Pombero. Then I was awarded. Then I got a Marie Curie Award with the Dr. Anna Peacock at the University of Birmingham. Then I moved to the Grams Chase group at the University of Hull as a visiting researcher. Then I got Royal Society Research Grant Fund to continue my molecular research, molecular imaging research. And currently I just joined as a PDRA with Dr. Andrew Bova's group and developing fatty acid metabolites, particularly for Alzheimer's diseases. Through creating, I'm very much thankful for all the funding agencies, including CSIR, UGC Kothari, FCT, and Marie Curie, Slowacka Curie Actions from the European Commission, and Newton Baba Fund and Royal Society of Chemistry. So thanks for your attention. Thank you very much.
Thank you, sir. Thank you for your wonderful lecture. And question, anyone has got the question, you can pose your question.
Thank you so much.
Madam, no questions.
Good evening, sir. I have a question.
Yeah, thank you. Yeah, please.
Yeah, I just wanted to know, as you told that MRI is water-based thing for detection of any abnormalities. So any substance which contains only water can be detected in this, or is there any other applications of this magnetic resonance imaging?
There are some other like fluorine 19, this kind of MRI also possible. There is a possible under parachest imaging agents also, for example, cobalt, nickel, iron 2+, these kind of compounds also we are using as a contrast agent. But we are going to detect some abnormalities. Mostly we have only water molecules in the body. That's why the water content only vary. So the varying amount of water content, and also because of the different chemical environment, like a molecular environment. For example, if you are considering as an for instance, breast cancer. So the breast cancer cells are, most of the breast cancer cells are overexpressed. The cells is overexpressed with pyrophosphatase. The pyrophosphate is one of the enzyme which is considered as a global or universal cancer biomarker. So because of the different overexpression of these biomarkers, there are the different, the water molecules also will vary. I mean the metabolites, during this process, there are the more number of metabolites also, concentrations and everything will be vary. So because of these variations in the metabolites will change the proton, I mean the
biochemical constituent.
Yeah, they can absorb the different amount of radiations, radio frequency waves. So based on that, then we are distinguishing the structure, where there is what is the depth and what is the size of the cancer and everything we are being detected.
Thank you, sir.
Thank you.
Sir, I have one question.
Yeah, please.
Yes, sir. Myself, Orgho, sir, from IIT Kanpur. First of all, nice lecture, excellent, sir. And I have one question. That you told that that is the work function of MRI is just based on the water. So in the, how in the normal cell and the cancer cell, water concentration varies, and how MRI just diagnose that is normal cell and cancer cell. Can you just summarize?
Yeah, that only I said is a good question. Actually, this actually the normal cells, the most of the time, the normal and abnormal cells has the same kind of phenomenon. I mean, same amount of metabolites, same kind of metabolic functions or process are being taking place. But sometimes, for example, if you're considering ovarian cancer, the ovarian cancer, it's need more amount of folic acid. You know that the folic acid is that's why if you are approaching for a hospital for any pregnant women, they are mostly doctors are prescribing the folic acid. The folic acid is very important. The folic acid receptors are overexpressed in the ovarian cells. Similarly, the breast cancer cells, there are the more amount of pyrophosphate and ATP. These are very, very important energy materials needed for the growth of our cell growth. Particularly, breast cancer cells needed more amount of phosphates. That is the reason 80% of the breast cancer women are highly prone to get bone metastasis. The breast cancer cells are they are metastasized into the bones. They will start to affect the bone firstly, then the other organs. This is the chance. So because of the overexpressions of the different environments makes the water and all the concentrations will change in the cancer cells and normal cells. So then we can concentrate if where there is more amount of pyrophosphate is expressed, then we can think that is the cancer. So if there is when we are comparing the amount of when we are comparing the amount of upregulated or elevated levels of the pyrophosphate or some particular metabolites, then we are differentiating the cancer, the abnormal and normal cells. So that the instrument is that is the advantage of the MRI, that easily distinguish the normal and abnormal cells.
Okay. Thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you so much.
Anyone else? Any question? Now, I just request all the participants to unmute the video. We would like to take the online photograph of all the participants for 1 minute maximum.
I can request Dr. Anbu to take up your presentation.
Okay. This looks like a sounding like stamping in the post office. I don't know some.
Jab Singh sir, can you hear me?
Yes, yes, sir. I can hear.
Sir, we can proceed. It's getting late. We have one
Yes,
more
yes,
lecture.
yes.
Yeah.
I have taken. Yes,
Yeah,
yes.
yeah. It's enough. We can move on.
Yeah.
Yeah.
Thank you. Thank you. Now we are moving to the last lecture. Now I invite Dr. Vijay to introduce the speaker.
Thank you so much, sir. Thank you. Thank you. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Thank you, Dr.
you, sir.
Thank you. We'll meet you
Thank you.
sometime
Thank
later.
you, sir. Sure, sir. Thank you.
Thank you, Dr. Ranbu. Hello, can you hear me? I'm Dr. Vijay.
Yes, sir.
Yes.
Yeah. May I know Dr. Pawan Kumar is online?
Yes, I'm online.
Okay, great.
Yeah.
Great. Good evening, sir. So it's my pleasure to welcome Dr. Pawan Kumar. We have had a lecture from the academician and also from a researcher from the academic institute. So now everybody is enthusiastic to hear a lecture from industry, from a person from the industry. So it's my pleasure to introduce Dr. Pawan Kumar, at present working as a principal scientific manager at GVK Biosciences Private Limited, Hyderabad. So Dr. Pawan Kumar did his BSc and MSc, BSc honors and MSc from Sri Satya Sai Institute of Higher Learning, Puttaparthi, Andhra Pradesh, India. Then he did his PhD in with Dr. K.C. Kumaraswamy at Hyderabad, University of Hyderabad, a well-known main group chemist. So he has worked with organophosphorus complexes for his PhD, and then he went to France for his doing his postdoc. So he did his first postdoc with at University of Bourgogne, Dijon, France, on the titanium complexes and checking their catalytic activity in a hydroamination reaction. And then later he worked as a CNRS postdoctoral fellow. So at the University of Paris, Marseille, in France. Again, he has worked with the phosphorus heterocycles and then immobilizing them. And then he has worked with Dr. Professor Frederick and Julian Luclia. So later he joined in August 2010 as a scientific manager and GVK Biosciences. And at present he is working as a principal scientific manager, GVK Biosciences. So it is our pleasure, sir, to invite you once again, and it's my pleasure to introduce. I hope the lecture will be highly useful to the BSc, MSc candidates and the research scholars and the faculty. for the emerging scientists. It will be helpful to the emerging scientists. Thank you for giving me the opportunity to introduce Dr. Pawan. Thank you. Please proceed, sir.
Thank you, Vijaykanth, for the kind introduction. It has been, I've been invited by Dr. V. Madhu. We both worked during our PhD in Central University. I come from an industry point of view. So most of my things are covered under IP and confidentiality. So I will not be able to present anything, but I will be giving you a perspective how life is after MSc, what are the options you have, what all you can do. Then you have, because I wanted this to be more interactive, so that I can answer your questions. You can stop me at any point of time it is convenient to you, or at the end of the talk it's fine with me. So as you see, I all came from like you all as an MSc. So that time we did not have so many options or so much of connectivity to know what are things available. So mostly after MSc, few options we had was finish your MSc, then we have an Asian Paints job which is ready for you, which will pay you 8,000. So we will more enthusiastic to finish our MSc, to get into the job. Suddenly after a few months somebody told there is something called IIT you can write. Then okay, let's start preparing for the gate. Then we all started preparing for the gate. So we wrote this one. Then suddenly somebody told, okay, there is a chance of getting into NEET CSIR where you can do PhDs. That time very few IIC, IICTs, few were there. So we started writing. We went almost with the flow, rather not knowing what can be done, what are the options we have. But slowly, but at this generation, I think very socially connected. They know a lot more than us. I will let you know what can be done. So I think the two speakers who would have presented regarding the academic point of view, the academic research, what you can do. So most of them for doing the academic research, you finish your MSc, then you start preparing for your CSR or a NET. You start getting a position, you start doing your research of your favorite area, whatever it is. Then some people are smart enough, they thought I want to go abroad, finish my PhD. So they start writing TOEFL, IELTS, all these things. They start applying for the American universities or the European universities to do the PhDs. So, but there are few people who wants to immediately start their jobs after MSc due to their personal commitments or whatever the reasons best known to them. So there are a lot of options which we did not know, but I wanted to, by this lecture, I wanted to give you an all options what you have after your MSc, which is very, very promising. As a chemist, it's very, very promising. After MSc, immediately after MSc, people can directly go into jobs. As I come from a corporate, GVK Biosciences, we go to all campuses for the campus placements. We immediately hire fresh MScs and get. So coming back to the pharmaceutical industries, there are two set of industries. Basically, one is a contract research organization, that which I work for. It is called a CRO. CROs are basically, we work with all the major drug companies. You take Merck, GlaxoSmithKline, Pfizer, Merck, you take any company, we work with them. What we do is, we as a company with the leading company, we sign a contract that we do the work for you. We work in delivering the future molecules, which are active molecules. It can be an HIV, it can be an Alzheimer, it can be any therapeutic area. A therapeutic area is one where you work on a particular disease. Each company specializes in that. So we as a company, we are into a service industry. A service industry means we get a work from them, we deliver to them, but we don't have any IP or we don't have any hold on it. Means even if it becomes a blockbuster drug, our service ends at delivering the molecule to them, but we don't have any patent rights on that. So that is crystal clear as a CRO industry. So we work with all the major companies. So sometimes in my 10 years career, I have worked on HIV, I have worked in malaria, I have worked on Alzheimer's. So different things, but I cannot disclose what I'm working because I'm completely bound by the IP confidentiality, which signature we do with the company. So what we do basically, the CROs in major CROs in India are basically GVK Bio, Syngene, AMRI, which is in Hyderabad, then Sai Life Sciences, which is in Hyderabad, Chem Biotech, which is in West Bengal, Jubilant Biosis, which is in Delhi. So these are the major CRO companies. So we work basically on small molecules. So they ask us, we deliver molecules which are in milligrams. What we do is they assign this is the molecule I want. We strategize with the chemical knowledge what we have, what we studied in MSc or we learned from PhD. We try to make a scheme how to synthesize. We do a retrosynthesis, take corresponding starting materials and make the molecules on a small scale. Immediately what we do is we ship them to the industry, to the corresponding company. Sometimes some of the work is also done at India, but what we do is they start checking the basic parameters, so the biological aspect of the molecule, how it is behaving, and for everything there is a standard. You have a standard drug which works in a certain way. When we make a new drug, what they do is how effective it is compared to the previous one. So they start checking the biological aspects. If they think that the biological aspect is very good, then they start going into in vitro, then they start going into animals, then it goes to a next level called human. uh, Somebody wants to have a question right now, or
Forward, you can proceed. Later I can ask.
yeah, no, not a problem. Yeah.
Yeah.
So what we do is, so we deliver small molecules, and as in an industry, it works in a fast pace. Means we have a certain deadlines. They give a molecule. They tell we want the molecule to be given by this time. So we strategize. We have a team of around 30 people who are basically an MSc chemistry guys who have experience, and they synthesize the molecules, and we tell them the report that how we are proceeding, and once the molecule is done, we ship to the corresponding company. So this is the first phase of research which a CRO does. So what happens is, so all the major companies work like this. Then once a molecule becomes active, means a company found out that this drug what you have synthesized has very good this thing against a particular disease, then what they start asking, can you make a molecule in a little higher quantity, because we wanted to test something else. So what we do is, we from a milligram scale to a gram scale, we usually synthesize and give them. But once that is done, and our main motto is how fast can we get the molecule. It is irrespective of what is the approach. We can start using a expensive starting material or an expensive catalyst to make the synthesis. That is immaterial at the start of the stage, because we wanted to get as many molecules which can be active. Out of lakhs of molecules, usually few of them found to be very active. So our goal is to synthesize a molecule, a target how fast we can do. So in this aspect, we usually don't worry about the yields. We don't worry about what route, how many steps we are synthesizing it, what kind of catalyst we are using it. So immediately we synthesize and give them. But once a molecule becomes an active, then the critical aspect comes into the picture. So the molecule is active now. I wanted to make this in a larger scale. When you wanted to make in a larger scale, if you start using all expensive materials, so the molecule itself becomes very costly, which is not affordable. Then they start looking at how can we optimize the process where we can get this molecule without using any expensive materials in a shorter route, and also not using any catalyst or reagents which are toxic, because sometimes the reagent what we use can become a toxic at a later stage. So that becomes, so here the next part of the industry comes into the picture, which is a process development industry. So what they do basically is, when we make a small molecule, so they start developing a process by which we can get these molecules can be synthesized on a multi-gram scale, maybe 100, 500 gram scale. So in this case, they also optimize what is the best route. Okay, we know this route, it can work, but where we can optimize, where we can use a better reagent, where we can shorter the synthesis. And also sometimes we try to use a reagent, sometimes we use an azide. Okay, usually azides are usually we try to do the reaction on a larger scale, sometimes they're explosive. Okay, we try to use, I think you start reading about butyl lithium, terbutyl lithium, secondary butyl lithium. So on a small scale, when we try to use, we have the safety measures, or the amount of, if something happens also, the amount of fire comes out is very less, it can be controlled easily. So but and when you go to a larger scale, the type of reagent what we are using becomes very critical, where you are going to do this reaction on a large volume reactor, sometimes large volumes of these things. So the reagent what you use also is very important. Sometimes we use a bitter lithium in my synthesis, but when you come to a larger scale, we feel that this reagent is not appropriate because we cannot use this in a larger scale. So they optimize what is the best alternative for making. So they do this kind of an optimization in the process development. Okay, the process development people try to deliver the same molecule what we have synthesized in a better way, and which is more affordable. Okay, in this case, once the process development is done, the chemical companies start testing it in different matters, in a different other kind of this thing on mouse, rat. They have different technologies and different platforms to test how this drug works. Once that and all happens, then becomes the molecule becomes an API. There are one more set of companies which work on active pharma ingredients. You know, paracetamol, a small molecule which we treat for fever. Paracetamol is the active pharma ingredient in all the medicines where we use for treating fever. So a company, once it becomes, all the tests are done, the molecule becomes active, they have the animal studies, the human studies, everywhere it gets cleared up, then we start making the molecules on a larger bulk scale. So there are companies like Dr. Reddy's, Laurus, Cipla, Ranbaxy, a lot of big companies are there. They work on a lot of active pharma ingredients, which constitute the main component of any drug. Once the API is done, they start using a sugar coating or a capsule or a syrup, whatever it is. They start, once an API is done, they do a formulation onto it, which released as a drug outside in this thing. So these are the two different kinds of industries what we work for. So after MSc, what are the options we have for a fresh MSc who has done an organic chemistry or analytical chemistry? What are the options we have after that? So after the MSc, when we come to a CRO industry, we have two options. One is a synthetic chemist. All the chemistry what we have studied during the MSc, the different kinds of reactions, different reagents, what we have learned in our MSc, we are going to start using them to make a small drugs. So synthetic chemistry, R&D, we usually come to the companies, we hire them, and as most of the universities, most of the universities does not have a better kind of an infrastructure to run all kinds of an experiments. So most of the MSc guys, except few universities, we learn a lot theoretically, but practically we may not have a lot of knowledge on how to perform a reaction. We may run a bitter lithium reaction, but when we start performing the reaction, a lot of safety measures have to be taken, how to quench it, how to use the reaction. If something happens, immediately how to use a fire extinguisher, how to handle it, all the SOPs, all things have to be learned. So what we do as a fresh MSc, a campus hire, we take them into the lab. We almost give them 6 months to 1 year training. Initial few months, we teach them what are the standard operating procedures. We attach them to a senior and teach them what are the different kind of reactions, how it has to be performed, what are the precautions to be taken, how it has to be quenched. Then we also teach them how to do a column chromatography, purification techniques. Then also we teach them what are the analytical techniques. Once you make a molecule, how to analyze that you have got the right compound. All these things will be taught in a 6 months to 1 year period. Then once we feel that they are confident enough in performing, we regularize them and put them into the system where they work for the big drug companies in synthesizing the drug molecules. That is one option you have for the synthetic chemist. A synthetic chemist, and also along with the analytical chemist, a synthetic chemist can also choose an option to become an analytical R&D chemist also. He does not have to do an analytical MSc chemistry guy surely can opt for an analytical R&D position, but usually an MSc chemistry who learns about the analytical tools and analytical techniques can also apply for this job. What they do is basically we synthesize a lot of molecules. So you go become an analytical R&D chemist where you have different platforms to choose. You can choose either an NMR, you can become a specialist in NMR, you can become a specialist in recording in an LCMS and a HPLC, or you can become a prep HPLC specialist, because prep HPLC is nothing but you make a molecule, an NMR guy records an NMR for you, an LCMS guy records the mass, whether you have the required mass or not. But sometimes, the purification of the compound becomes challenging. Prep HPLC is a preparative HPLC. I think you have learned about TLC, you learned about prep TLC. The advanced technique we use is a prep HPLC, where you take an impure compound which have UV activity, you try to separate, make the pure compound out. So an analytical chemist has these kind of options. Once he wants to become an analytical chemist, he has different options to choose. And this jobs does not require a PhD. All MScs can come, and it is very lucrative. And once you have a few years of experience, you become a hot cake, and you have a lot of options, and a lot of companies take you, and they are very critical part of the industry. Similar to a synthetic chemist, after few years of experience, once he knows handling different kinds of chemistry and how to perform things, your experience adds on, and you can grow into the organization. Okay, then these are the synthetic R&D positions what you have. But as I talk, there is another kind of an industry where they work in process development and also doing a bulk drug synthesis, where here the chemists also have few options. One is quality assurance. It's called QA and quality control. Okay, QA QC it is called in a short form. Here also you can opt as an MSc chemistry. You can come. Most of this API companies like Reddy's, Loris, or even Arabindo, Matrix, all these companies, they also hire you. They give you a training. Quality assurance is basically once you make a molecule, once you make a process out of it, how good they are following the protocol in synthesizing it, what is the quality of the material what we are synthesizing. Okay, all these aspects come into the quality assurance. Quality control is what are the control measures we have put in place to check whether the compounds are taking out in the right platform, right analysis is being taken. All these things are there. There is one more aspect where an MSc chemist can choose is the regulatory affairs. Regulatory affairs does not involve dealing with chemicals or even dealing with the analytical instruments. It basically deals with the SOPs, means once you make I make a molecule, a drug company makes a molecule in a larger quantity. So once you make a molecule, you have a process which is very specific to you. It has been it means you are the only owner of the process. What you do is you patent the process so that nobody can copy you, so that till certain years only you can use the process, not nobody else. This regulatory affairs controls all this patenting process, the IP confidentiality, and once you make a molecule, what is the process has been used from the start to end, all the filing, because this is very important for filing a patent or duck counter authority. When you wanted to make this, all these things are very much required. So the regulatory affairs person takes care all this part of documentation part, which is very critical, because you try to make a small error in the documenting what you have done, you can get into trouble. So these regulatory affairs people are very critical part of the industry, where they take care of all the documentations. So as an MSc chemist, these are all the options you have after doing your MSc. So many people don't know this, but I think there are industries basically located in Bangalore, Hyderabad, a few in Tamil Nadu, but Hyderabad is hub for a lot of big companies, Gujarat. So there are different kinds of companies, means people don't want to go into academic positions. These are all the options you have. This is the gist of what I wanted to tell. But as it being a more interactive session, I wanted to hear from you so that I can answer a lot of your questions or anything better you wanted to know. I am ready to answer that.
Avan, it's a nice presentation. And suppose if we want to send our MSc students,
yes.
So if I ask as your person of GVK, so if people will come to our campus and recruit the people, is there any provisions like that?
Yes, because at one point of time, we usually now for this year, we have done it last year. We traveled to almost majority of the states who were interested to come. So we go to all the major, sometimes if your university calls, we go to all the major universities, central universities, JNTUs, Andhra University. So if there is an interest from your university and the number of people are more, you can even put an advertisement to tell all the local universities nearby you. You tell there is a substantial amount of people who can come for a campus placement. Then we connect with the HR and we come to your university, conduct a test there. Immediately we screen them and select the people for the interviews and do the interviews in a day or two. And then we list out and take them to the company.
Okay, good, very good.
So thank you, sir. Sir, is there any possibility for internship with the stipend for MSc students when they are doing their second year course?
No, because we come from an industry where IP and confidentiality becomes very critical. Usually we don't take interns. And not something is payable because we cannot do that.
Oh, thank you.
Yeah.
Good evening, sir.
Good evening.
Sir, you were telling this opportunity will be for only MSc chemistry people. Is it, or actually there is an emerging field nowadays that is MSc forensic science, in which we are dealing with those analytical techniques, the ones you mentioned, the HPLC or
yes.
Yeah. So, do you provide anything for MSc forensic science students also?
No, we don't provide. We are in an industry. We take an MSCs. We don't give any training. We hire them. So once you become this thing, because you've learned a lot of techniques, once you come to an industry, you have a hands-on experience of using all the instruments. If you wanted to choose an HPLC or this thing, once you get an 1 to 2 years of experience, then you can choose whichever field you want. You want to go to forensics, because basically the instrumentation is same. You use the HPLC everywhere. You use it for the purpose can be different. I use it for an R&D purpose. You wanted to analyze a drug, or you want to analyze for forensic purpose. It's the same thing. The analytical technique is same, but the platform what you wanted to use, that you can choose always. But yes, tell me.
So it will be valid for also MSc forensic science students.
Yes, if you have studied analytical chemistry,
yes,
you have done about this thing, yes, you are eligible. You basically answer the questions what you have learned in your analytical chemistry. We take you and we train you.
Okay, so there is not mandatory that there should be MSc for chemistry people.
No, MSc chemistry. That's what I told, that even MSc chemistry, MSc, you can also specialize in analytical chemistry or even forensics. If you have learned about your analytical techniques, you can surely attend the interviews. That's not a problem. Yeah.
Thank you, sir.
Yeah.
So what about the salary package when you gave for during those training period?
It is around something close to 18 to 20,000. 18,000 to 20,000 we give for a fresh MSc. because we train them. And we also expect them to stay with us at least for 2 years. I think that is minimum because they learn, because usually some people jump immediately after 6 months. We invest a lot of money, and the infrastructure what we provide is one of the world-class infrastructure, because we work with almost the leading drug companies. So we have to maintain certain kind of a standard of the labs. So I cannot show you the pictures because of confidentiality, but just imagine you have a world-class infrastructure in these companies. The kind of infrastructure we have is far, far better.
Dr. Pawan, this is Nandakumar from Karanya.
Yes.
Thank you for your insights on the after MSc chemistry also.
Yeah.
I have a basic question, since because you're working in a drug industry.
Yeah.
My questions is like different companies. For example, if you take Ranbaxy, Pfizer, Zydus, Cadila, etc.
Yeah.
Everyone come with the same composition of the drug, but the problem is the rate differs.
Okay.
So ultimately, what the doctor prescribes, we go and get it.
Okay.
But for example, if I take a tablet, recently I got Moxicine and Moxclave. So Moxclave from Ranbaxy, Moxicine from Zydus. Both have the same composition, but of different price. Why is that so?
Basically, a formulation is patented by them, because usually the price becomes, if you wanted to make what are you talking about is basically formulation. Each person, the component is same. There is a slight change in the formulation, and they have their own patent for that.
Okay, so if the composition is changed, the drug's activity is changing, right?
The activity is changed.
Yeah. So
they
the
usually have
composition is same.
They have a small difference here and there.
So because of that, the rate differs.
The rate differs, and means how did they get to that, and what kind of rights they have on that. Means it can have a small efficacy differences, and also a brand, as like you go make an Adidas, you in Chennai you have a bigger industry of cloth industry, but the same thing what makes in Chennai, it comes out of the company. What you make it, you sell it for 10 rupees, I sell it for 100 rupees. A brand comes into the picture. So this branding differs, as you rightly pointed out. The composition is same, but once people wants to prefer a Ranbaxy rather than a smaller company, but so there the brand picture comes into the picture. That's why the cost also differs.
That's fine, sir. But in health sector, that should not be the case, right? In
others, but that is happening. Sorry to say that, but it is happening. There are people who go with the brand, so that's why these issues come into the picture. Otherwise, once it becomes a generic compound, it becomes very cheap. It has to be affordable to all of them in the same way. And if I'll tell you a right thing, a company like Ranbaxy or Zydus Cadila makes a formulation which as a drug, means you make the whole drug, syrup, say, it costs you 60 rupees in India. The same syrup, they make it for a foreign company. The brand name and this thing differs, because it goes to US. It is sold for $150 to $50 to $100. So it's basically a pure marketing, and they wanted to make money out of it. It's nothing to do with ethics and morals, and nobody is worried about the common man.
Yes, sir. Thank you.
Yeah.
Hello, this is Dr. Vijaykan. In continuation with Dr. Nandakumar, what he told.
Yeah.
But one of my relatives, it's happened 2-3 years back.
Okay.
For a child, he had some problem, but he prescribed one medicine. 2 days, it is not subsided whatever the disease.
Okay.
But suddenly, the doctor himself has called my relative and asked how the child is.
Okay.
He told not much improvement. Then he changed the tablet. Brand is different, but the composition is same. But it got cured.
Yeah.
So the brand is same. Brand was same. The composition was same. Brand was different, costlier one. But it got it got cured. Yeah, I know the case.
I will tell you one interesting thing. My friend Madhu also knows. One of my friend works in IICT. Is a pharmaceutical supramolecular chemist. Means he basically solves crystals. So he is more interested into looking at pharmaceutical components. So he got one of the molecule, one of the API he wanted. He got a strip of medicines which is available on store. He got the molecule and just grinded everything. You get few milligrams of the API, this active pharma ingredient. He grinded it and extracted the compound. He did not get anything. He just got sugar. Just imagine, this is cities. There are in the villages, there are people who sell tablets which are sugar coated tablets. That's all. It does not have the active pharma ingredient which cures the disease. So these things happen a lot. So that's why when this comes into the picture, somebody wants to believe, okay, a big company like a Ranback Seam or this thing cannot do the same thing like a smaller company, because they are protected and they are into the public listed system. Somebody does anything like that, there is a public scrutiny. Government come into the picture. As a citizen, you can even question them because they are a public listed company. So all these things, that's why when you wanted to buy a drug to be authentic, you try to go for a brand keeping all this in mind.
Okay, one more question, and based on that is for the student point of view, I'm asking.
Yes.
Okay, so you excellently you told about the, for example, N-butyl lithium doing in a small scale and large scale. So we have to take the precaution that will be highly useful to the students.
Yeah.
But one more thing is also I came to know in not for the regarding the because of the safety measures of the small scale or the large scale, but sometimes in the some of the things which are working in the small scale, in large scale there may be a hot spot or cold spot. So sometime it may not work in the because of the stages. So apart from the reagent, what the safety precaution of the reagent, any other things should be followed. So that as at the MSc when you are coming out, if they know about these things also, some of the things will it be helpful when you are they are joining the industry.
Because when you want to do in a small scale industry, we just not worry about a lot of things. But when you want to do it in a bulk scale, what kind of energy is being released, whether the pressure can be sustained or not, all this lot of enthalpy, whatever we read, what kind of energy comes out, what kind of gases come out, what kind of pressure is developed, all these things, aspects have to be taken care, which a process development guy takes into the picture. See, when you're trying to do a reaction on a small scale, you can stir it with a magnetic pellet. Okay, to attain certain kind of temperature, we just try to heat it. It's okay. But when you go to a larger scale, the same heating, if you try to, it has to be done in a very controlled way. If you don't do it, there can kind of an explosion, or the energy released from the system can have a very drastic impacts. All these things have to be studied in between, but these are not taught in MSc. But once you become once you can directly choose to be a process chemist. In that you are taught all these things, and there are process engineers who are basically doing a chemical engineering study. All this, they study the energy aspect of it, what energy, how do you do, if you do it, what kind of these things, and if you want to do this reaction in a autoclave or a reactor, what kind of problems can be faced, how the mechanics can be done, and if there is a certain kinds of gases delivered, how to release the pressure from it. All these things are studied by the process engineers, who are very critical part of the process and the bulk industry.
Yeah, thanks. That is what I wanted to know. So that is the students MSc with the MSc chemistry, they can also be absorbed in the process industry. So
yes,
the
yes.
Engineers mainly working on the process. I think so.
Yes.
So the chemist can directly they can absorb in the process in industry.
Yes, because you can choose. Because for girls, basically now at one point of time when I started my career, the number of girls population was only 10%. But now I see there are 30 to 40% of girls coming into R&D industry also. But mostly they don't prefer process because it is to deal with lifting a lot of heavy RBs and these things. So usually they choose R&D. But most of the guys, if they have interest in a process, they directly join the companies who are doing process chemistry only.
Okay. Okay. Thank you.
Thank you, sir. Thank you so much for a valuable, very interactive, lively session. Now we are coming to the closing session. Now I invite Dr. Emmanuel to propose the vote of thanks.
Good evening.
Just thank you for all for giving me this opportunity, and I have all my details with Madhu. Anyone, it can be a faculty, it can be a chemist. Anybody wants to come to industry, you can surely contact me. Not a problem at all.
Thank you,
sir. Thank you.
Good evening to one and all present here. It's my pleasure and privilege to propose the vote of thanks on behalf of the Department of Applied Chemistry, Karunya Deemed University, First of all, I remember the Almighty God with a heart full of gratitude for enabling us to organize such a web seminar, the large number of participants amidst the corona pandemic. On behalf of the faculty members and all the participants, I thank the guest speakers, Dr. Venkatakrishnan, Dr. Andu Challamuthu, and Dr. Pawan Kumar for their valuable lectures. All the three lectures were highly motivating, well crafted, and tailor-made for the occasion. I appreciate and thank the guest speakers for their zeal to share knowledge with us. I am sure that your lectures would be very useful to participants in their higher studies. Thank you very much, sir. I would like to express my gratitude to the Vice Chancellor, Pro VC, and Registrar of Karunya Deemed University for their constant support and encouragement. Especially, along with my colleagues, I thank our Dean, Dr. Joseph Kennedy, who always cares for the Department of Applied Chemistry. We are sure, under his guidance and leadership, we would reach greater heights in the near future. Thank you very much, sir. I thank the Department of Computer Science and Technology for providing the online platform to conduct this webinar without any technical problems. I thank all the participants for making this webinar a grand success. Without you, we could not have achieved this milestone. Thank you very much, dear participants. Last but not least, I thank all of my colleagues for their cooperation and helping hands in the promotion and all other activities for the successful conduction of this webinar. Especially, I thank the conveners, Dr. Madhu and Dr. Bijal Singh, for organizing the webinar in a wonderful manner. Thank you, one and all, once again. Have a great weekend ahead. Thank you.
Sir, the feedback form is not working.
Sir, the feedback form is asking you need permission after submission.
Yes, sir. We cannot open it.
Feedback form is not working, sir.
It's asking permission, sir.
They will sort it out, and now I invite Dr. Rajendra Kumar sir for the closing prayer. Dr. Rajendra Kumar. Okay, we'll close with the word of prayer. I'll pray. Father, we thank you for this time of interaction, learning, for almost 3 hours. So Father God, thank you for all the participants. Thank you for the 3 wonderful resource persons that you have brought, oh Father God, and helped us to learn many things. And also for the interactive session, oh Father. We thank you, Lord, for our conveners who arranged it with so much difficulties that it went so well, oh Father God. Father, we want to thank you, and also, Lord Father, for all the participants, oh Father God. We keep everything at your precious feet for helping us from the starting till the end, that your grace was upon us, oh Father. Thank you for helping us to learn. We pray this prayer in Jesus' name. Amen.
Dear participant, we came into the last part. The information is most of you are texting us that the feedback form is not opening. We will check that internally. Probably within a 10 to 15 minutes time, you will receive the email from our organizer with the feedback form link. So you can give your feedback. That will be taken consideration, and immediately after that, you will get your e-certificate in your mobile. In your email. Thank you. Thank you very much. Have a nice day. Stay safe. Thank you.
Sir, thank you, sir. Sir. The meeting is
Thank you, sir.
Thank you, Mindal. Thank you, Dr. Madhu and Dr. Jabbar Singh, for arranging it.
Thank you, madam. Thank you.
Thank you, Jema Singh. Thank you,
Thank
madam.
you, sir. Thank you. Thank you.
Thank you,
We can leave,
Thank
sir.
you all. Thank you
Yeah.
all. Stay
Yeah.
safe during the
Yeah.
pandemic. Thank you.
Thank you.
Thank you, sir.
Thank you, other faculty member from other institution and a research scholar from keep rocking. Thank you.
Thank you, sir, for nice session. It's our pleasure.
Thank you, Rizav. Thank you.
Sir, can we leave now?
Yes, you can leave.